Friends, kindly maintain the silence. We are about to begin the session.
Powering the future, one binder-free electrode at a time. Now I would like to invite Dr. M. Lawrence, Assistant Professor of Physics, St. Joseph College, to chair the session on innovative polymer electrolytes and binder-free electrodes for energy devices.
Good morning to one and all gathered here. It gives me immense pleasure to introduce the speaker of this session, Professor Dr. Ramesh T. Subramaniam. He is a distinguished material scientist at the Department of Physics, Faculty of Science, University Malaya, Kuala Lumpur, Malaysia. His research focuses on developing solutions for energy storage and harvesting devices aimed at promoting clean energy and sustainable smart cities. Notably, he has pioneered the innovation of highly adhesive polymer membranes, self-healable hydrogel electrolytes, and environmentally friendly polymer electrolytes. Throughout his career, Professor Ramesh has received numerous accolades, including election as a Fellow of the Academy of Sciences in 2023, marking him as the first Malaysian elected under the field of physics, astronomy, and space sciences. Fellowship with the International Science Council in recognition of his contributions to science as a global public good. The Pacific Young Scholar Award from the American Chemical Society, the Young Scientist Award from the International Union of Pure and Applied Chemistry, Fulbright Fellowship at Princeton University, United States of America, Distinguished Fellowship at the Institute of Advanced Studies, Durham University, United Kingdom. In 2021, the Nobel Committee for Physics invited him to nominate candidates for the Nobel Prize in Physics, underscoring his standing in the scientific community. Additional, Stanford University recognized him among the world's top 2% of scientists for career-long citation impact. Professor Ramesh has an extensive publication record with over 335 journal articles, 6 patents, and 8 book chapters. He works as a total citation of 17,862 and an H index of 72. He has secured more than 86 research grants, totaling over RM25 million, and has supervised numerous postgraduate and undergraduate students. Professor Ramesh's work continues to have a significant impact on the advancement of material science, particularly in the realm of sustainable energy solutions. Please join me in welcoming Professor Ramesh to take over the session. Welcome you, sir. Thank you.
Thank you, Mr. Chairman. Can you hear my voice clearly?
Yes, sir. It's okay, sir. I think, yes.
Okay. Can you see the slides as well?
Yes, sir. It's not in the slideshow, but
Yeah. I'm okay. Now is it fine?
yeah, it's good, sir. Thank you.
Okay. Again, thank you very much for the Mr. Chairman, and also I take this opportunity to thank the organizing committee to inviting me, and a special thanks to my postdoc, Dr. Prasant Kumar, for connecting University Malaya with your esteemed institution. Okay, today I'm going to give a talk on innovative polymer electrolytes and binder-free electrodes for energy devices. So from the topic itself, we can say I'm going to focus on the two main ingredients of the energy devices, which are electrolytes and also electrodes. So before I go further details, my name is Ramesh T. Subramaniam. I am from University Malaya. So my official website is given there and my email also given there. So you can contact me anytime if you want. And also, like I'm an Indian origin and a Malaysian citizen. Like I'm a third generation in Malaysia. Okay, my talk I've divided in three segment. The first segment I'll focus on introducing my university. Second, I'll talk about the technical aspect of the research that we are doing. And the third sections will be more on the opportunities that will make us to collaborate in future events. Okay, first, University Malaya. So you can see the main thing of the University Malaya is we call as a home of the bright and land of the brave. And University Malaya is established in 1905. So this university is more than 100 years old, and it is started as a King Edward VII College of Medicine, Singapore, then became as a Raffles College of Singapore. Then in 1962, University of Singapore and University of Malaya become like a two university when Singapore separated from Malaysia to become as a country. And we have our own hospital, and this called as a university hospital, opened in 1968. So we got an established faculty of medicine with a unique hospital attached to it. Okay, here are the vision and mission of the University of Malaya. So the vision is a global university impacting the world, and the mission is pushing the boundaries of knowledge and nurturing aspiring leaders. And some of the flag bearer of University of Malaya, you can see that University of Malaya is ranked number 60 under QS World University Ranking, and also ranked number 11 under QS World Ranking University in Asia. And we also established very high ranking in the green metric, where the university is establishing quite a number of green applications, green technology, and also the green campus concept. Okay, here are the UM profile. We have 14 faculties, 2 academies, 2 academic center, 4 research clusters, more than 70 research centers, and more than 200 academic programs with the 2 institutes. And our approximate number of undergraduates is 20,000, with the postgraduates around 14,000. So you can see the ratio of the undergraduate to postgraduate is 1:1. This is due to the concept of the University of Malaya by the government of Malaysia to make it as a research university. And we got a many international students as well as international academic staff. And we have a broad-based research intensive university programs where we got like 77 undergraduate programs, around 150 master's degree programs, and 28 doctoral degree programs, 2 double degree programs, and 3 dual master programs on top of 6 collaborative PhD programs. So here you can see the faculties and institutes involved in University Malaya. And we also got like 4 main research clusters. So our research are focused on these main 4 clusters. The first one is social advancement and happiness. Second is health and well-being. And the third one is frontiers of the natural world. And the fourth one is innovative industry and sustainability science. So these 4 clusters will cover all the research that focusing in University Malaya. And we also promote multidisciplinary and interdisciplinary research among the academic staff. Okay, this is our beautiful campus. You can see here. And our faculty of science is located here. And you also can see the University Malaya is very close to the capital city, Kuala Lumpur. So you can see the capital city of the Kuala Lumpur and the satellite town we call as Petaling Jaya. So it's very close to the, or I can say part of the campus is inside the capital city. And we got a very beautiful lake and the whole campus is very green and a lot of natural. And I also wanted to introduce to you all the Institute for Advanced Studies, where I'm the dean for this institute. And this institute also provide quite a number of multidisciplinary and interdisciplinary research. So you all are always welcome to visit the campus and also the institute. Okay, now I go to the second part of the talk. This part of talk, mostly I'm going to concentrate on the technical aspect. So first of all, what are the motivation of our research work? If we all know, the 2019 Nobel Prize in Chemistry was given for the development of lithium-ion batteries. And now researchers are looking what is next, what is after lithium-ion batteries, how to make it even better. In line with that, if you look at the 10 predictions for the next decade, published by the world in 2030 by Capital Group of USA, we can see three things are much of our interest. The first one is autonomous vehicles will hit the fast lane, green machines will rule the road, and renewable energy will power the world. Okay, here you can see like two different cities are portrayed. So one is a sustainable smart city. The other one you can see like a very congested city. All of us will love to live and stay in a sustainable cities like shown in the picture. Okay, what it meant by sustainable smart cities. So cities with the parks, green spaces, solar power buildings, good quality of life, space for nature, then eco-friendly of the public transport and transit system. And on top of that, also focusing more on the solar energy usage. And when we talk about the smart cities, these three things we cannot separate. The social aspect, economic aspect, and also the environmental aspect. So our focus is on transport system, specifically on energy storage system for electric vehicles. And our target will focus on these three dimensions where environmental and economic aspect of smart, sustainable cities to reduce air pollution and carbon dioxide emission and also create job opportunities. Okay, one of the new devices that we introduced in our lab and we are working a lot is on supercapacitor. So from the name itself, you can see supercapacitor is a combination of a supercapacitor and battery. So this is considered like the future of the energy storage solution. So for this type of energy storage devices, we use asymmetrical electrodes. We also can call this as an asymmetrical device because one side we will have a binder-free battery type electrode and the other side we will have the capacitive type of electrode. And these electrodes will be separated by a electrolyte. So in this talk, I'm going to share with you all the electrode materials and the electrolyte materials that we are fabricating or formulating in our lab. And the materials used for these type of prototypes are cheap and abundant. And not only that, these supercapacitors can be constructed in a different design. One can be rigid and the other one can be very flexible. Okay, here are the three drivers that promote the investment in energy storage because we need to have a proper stakeholders to invest money on this kind of a research. So the first due to the increase in the electricity bill and growing dependence on the fossil fuel and also decarbonizations. On top of that, you can see the Ragun plot here shows that supercapacitor generally shows high power density and less energy density, whereas batteries and fuel cell will show high energy density but low power density. So there is a huge gap between supercapacitor and batteries in terms of power and energy to be produced simultaneously. So to bridge this gap, we are introducing a new type of device called a supercapacitor, which can bridge the gap between supercapacitor and battery. Okay, next. This one in terms of the Malaysia. Malaysia's carbon dioxide emission in 2020 increased 69% compared to year 2000. And there are four main contributors. And one of the main contributors is the transport industry. So how can we contribute to reduce the carbon dioxide emission? So one of the way is by using electric vehicles. And most of the electric vehicles currently available are powered by lithium-ion battery technology. And the drawback here is current EVs takes 4 hours to fully charge. So whenever we talk about electric vehicles, the distance and times are two crucial things. So we must have a proper device. So when I said energy storing, I already explained to you about the supercapacitor. And we are also working on the energy harvesting devices like a solar cell. In later part of my presentation, I will also share with you how these two energy storing and energy harvesting devices can be integrated. There are some important research works on EV culture from Malaysian perspective has been conducted. Because most of the time, the consumer thinks electric vehicles are very expensive. So we did analysis on consumer to EV purchase intention. And the key outcome shows most of the undergraduate are interested in electric vehicles. And also we found that people between the age of 35 to 45 also interested in EV. So these kind of studies shows there are good future for the electric vehicles. Next, electric vehicles means always people think the cost is very high. So here, a summary of the estimated cost of electric vehicles in 2025 in USD. So when we talk about the cost, there are three main things important. One is direct cost, the other one is indirect cost, and the third one is battery and power electronics. The direct cost and indirect cost is quite difficult to reduce. This one more for the marketing aspect. For researchers, we can concentrate on battery and power electronics. So if we find the cheaper materials and which sustainable materials, by reducing the price, we can actually reduce the EV price by nearly $7,000. So here you can see how we reduce the battery pack cost. So in other words, the importance of developing new materials for electrolytes and electrodes are crucial in a way to reduce the price of the energy devices. And in Malaysia, we also got our national automotive policy. I'm sure the similar kind of a policy will be in many countries, those who are promoting their electric vehicles. Among the list of technology for the development projects under the policy, you can see the main thing is development of advanced electrode and electrolytes for lithium-ion battery charge. So that means the government are focusing on the electrode and electrolyte. And also the second one you see means the next generation battery technology. This is in line with what I mentioned earlier. So to see what are the next invention, we can bring it towards the battery technology. Okay, how is this device related to the policy? It supports electrification. We can produce new type of a supercapacitor that would have a longer lifetime and longer drive distance. And also we can produce novel electrode and electrolyte to fabricate supercapacitor. Okay, now I'm going in details about the electrolyte, electrode, and device. When we talk about electrolyte, most of the devices are using liquid electrolyte. If you see this liquid electrolyte, they are harmful and prone to leaking. If you check your handphone battery, if it is mentioned as a lithium ion battery, it means the electrolyte are in the liquid state. So to overcome this, we can introduce solid polymer electrolyte. But the problem here is polymers are insulators. So how to make this insulator become as conductor? So that's where it becomes as a solid polymer electrolyte. But the problem here is when we make a solid polymer electrolytes, when we sandwich them with the electrode material, the contact can be an issue as well. So this will create the low ionic conductivity, and this will lead to the lower performance of the devices. When we talk about the electrode, the conventional method for the electrodes are by using binder. The famous binder they use are polyvinylidene chloride, where these PVDF are also insulated. So these kind of materials increases the resistivity and also the addition of the dead weight. So that is where we are promoting the binder-free electrode. So we see how to overcome the electrolyte, electrode, and also the device. So the device part, I already explained to you earlier itself. Okay, here are the evolution of the polymer electrolyte. The reason we are using lithium, because if you look at the periodic table, after hydrogen, helium, lithium is the lightest. And when you use a lithium salt-based polymer electrolytes, the conductivity can be increased about 10 to the power of -5 Siemens per centimeter, but the conductivity is still not sufficient to be used for the energy devices. That's where comes the second generation, which we call as a plasticized salt-based polymer electrolytes. When we use a plasticizers, the conductivity increased. For those who are not familiar with a plasticizer or plasticizing effect, it's something like you're adding water to the clay to make the things softer. So what happened here for the second generation, the conductivity can be enhanced, but the materials become too soft. So the mechanical properties deteriorated. So this becomes difficult for us to handle and to fabricate devices. That's where come the third generation polymer electrolytes, where you use a nanocomposite materials like aluminum oxide, silica, zinc oxide kind of materials to improve the ionic conductivity. These nanocomposite not only increase ionic conductivity, at the same time, they also can improve the aging effect. When I say aging effect means this one, they can retain high ionic conductivity with a prolonged time. In progressive years, we are using like a radiation and also adding of ionic liquid and carbon nanotubes. Ionic liquids is another materials that we can use to increase the conductivity, where we can replace the conventional organic solvent. So they will create more amorphous and increases the ionic diffusion. And the addition of ion liquid with a bulky cation will produce high concentration of iodide ions in this case, because we are using sodium iodide as a salt. Okay, next, when we talk about polymer electrolytes, like I mentioned earlier, the contact is always the main problem because of the nature of the materials. So when we produce hydrogen electrolyte, they became more like a double-sided tape where they can stick very well with the electrode materials. So hydrogels are three-dimensional hydrophilic polymer network. We can make them in a physical cross-linking, or we also can make them in the chemical cross-linking. So they call as a physical hydrogels and also chemical hydrogel. For the chemical hydrogel, there will be a new covalent bond will be formed. Okay, here are some of the examples. So for example, polyvinyl alcohol. We can purchase polyvinyl alcohol from the supplier itself. Or just say we want to make them as a hydrogel. If we follow the steps given here, like by selecting the appropriate initiator and appropriate cross-linking agent, we can convert the polyvinyl alcohol to become as a hydrogel polyvinyl alcohol. We can do this for many different type of polymers, even like a natural, or even we can do for the synthetic polymers. Here, like a natural polymer, like a chitosan, cellulose, guar gum, all these things also can be converted to become as a hydrogel polymer electrolyte. And hydrogel electrolytes are highly stretchable, flexible, self-healable, hydrophilic, thermally stable, and also compressible. So here you can see hydrogel of acrylic acid. So you can see we can twist them, we can bend them, we can even do the knotting, we can even stretch them more than 200%. Here is the self-healing properties of hydrogel. So for a hydrogel also, we can cut to make them as like a two pieces. So when you let them to connect together, due to the cross-linking properties, they can perform as well as before we make them as a two pieces. So this shows that they got the natural self-healing properties. Here are some of the results. So you can see like a polyacrylamide hydrogel, we add with the ammonium persulfate initiator and sodium montmorillonate, the clay as a cross-linking agent. So the right hand side, you can see the flexible hydrogel, how sticky the material is look like. And here are some of the FACM results. They shows the porous morphology of the hydrogel electrolyte. So these are very useful for the transportation of ions. And IDEX also confirm the presence of the acrylamide in the materials. And the hydrogel electrolyte shows that the modified polyacrylamide with having the branch chain and also by adding another conducting polymers will show better performance compared to the pure polyacrylamide hydrogel electrolyte. Okay, next, let me go through with some of the electrode materials. So when we talk about electrode materials, we need to study about the porosity, conductivity, doping, composite, and nanosize. So here you can see I'm going to share with you the ternary nanocomposite for electrode materials. So the base will be like a nickel phosphate and then become as a nickel phosphate and silver phosphate. And for the ternary, we add with the polyaniline, pani nickel phosphate, silver phosphate. And we also did the optimization and fabrication of the binder-free nickel copper phosphate electrode using microwave assisted hydrothermal method. So here you can see the reason we are using like a nickel copper phosphate, because this combination will give us a binary metal phosphate framework which decrease the band gap and provide the electrode material with a higher electrochemical performance. And the phosphate will give excellent electrochemical performance together with the low resistivity and high chemical and thermal stabilities. And here, if you see hydrothermal method, generally will have excellent properties. Sorry. Okay, if you see here means like they show excellent properties, and the hydrothermal method is actually, even though they are excellent, but they are energy consuming and they will take a longer synthesis time. So these are based on the conventional heating mechanisms. So what we are doing here is we are combining the hydrogel route with the microwave heating. So this is known as a microwave assisted hydrothermal method. So this will reduce the reaction time, and also the rapid reaction time of microwave heating leads to less energy consumption. And next, you can see, once we got this microwave assisted hydrothermal method, we will use the design of experiment to optimize the condition needed for the experiments. So here you can see, for example, the temperature range can be from 90 to 100, or time can be from the 5 to 20 minutes. And the nickel copper ratio also, we have a few ratios. And this range and the ratios are based on the literatures. So based on this range, then we will do the DOE to find out the optimized temperature, time, and the ratio. And from here, you can find the best formulation will be the temperature at 90 degrees Celsius, time about 12.5 minutes, and the nickel copper ratio will be 3.1. So once we find this or we optimize these values, then we go ahead with the further characterization and formation. And another new materials that we are working in our lab is magazine. So magazines are flexible 2D layered porous hydrophilic materials with highly electronegative terminated groups. And here you can see the magazine. So we are using like a ball milling. And previously we can see magazine actually made from the mag space, where M is from the metal and A you can see from the non-metal materials here, and X will be either carbide or nitride. So this is the combination we make the magazine. And this magazine will be make in the plasma treatment as well. Then exfoliation will be conducted to get many layers. So this will increase the surface area of the magazine, which will help in the performance of the devices. Okay, one of the main concept we are doing here is innovate here, make here, and deploy everywhere. And since these are solid state materials, so this enable the 3D printing, and also this will be very useful for the 5G technology. On top of that, since most of the time people wanted to find out the safety of the electric vehicles. So since we are focusing on the electrode and electrode materials, we are also proposing EV battery passport. So this EV battery passport will have the detail about the electrode materials and also electrolyte materials and their safety data sheet and the safety of the materials, so that this will convince the customer to purchase the electric vehicles. Next, I'm also going to share with you the all-in-one configurations. When we said about all-in-one configuration, this is focusing more on the contact process. Like we mentioned earlier, the electrode and electrolyte cannot be sandwiched together because of their contact issues. For this all-in-one configuration, you can see here, for example, just say we got a polymer like a PVA and agar. First, we make them as a solution. Then we make them as a film. So once we make them as a film, then by using appropriate initiator and cross-linking agent, we make them as a hydrogel. So once we make them as a hydrogel, next we grow electrode on top of the electrolyte. This is done by addition of aniline and pyrrole, and they will polymerize, and the pani and polypyrrole will cover the electrolyte on the surface. Once done this, we got a materials like this. So you can see from this material, we cannot differentiate the electrolyte from electrode. So they all look like one piece of material. And here, one of the new projects that we are working on, where we are trying to integrate solar cell energy housing devices together with the energy storage devices. Like Malaysia is in a, what you call like a equator, and we get sunlight throughout the year. So during the daytime, the energy will be stored from the generated from the solar cell will be stored in the energy storage devices, and this can be used in the nighttime. So this can be done by using the similar electrode material. Okay, now at the end, to conclude, the three take back home message from my presentation. The first one is electric hybrid vehicles are better than petrol diesel vehicles in terms of fuel economy, noise, and emission. The manufacturing cost of supercapacitor can be lowered if we focus on appropriate innovative materials of electrode and electrolyte. And supercapacitor can be used in electric vehicles as a energy storage devices. Okay, now the third part of my presentation. I think since I'm an invited speaker for this conference, so one of the main things for this kind of a conference is a networking and sharing the opportunities. So let me last part to share some of the opportunities internationally available and also in Malaysia, so that this can be a platform for us to work in future with the many new adventures. So the first one is about the Fulbright program. So when we talk about Fulbright program, this program is based in US, and I know India is also a part of this Fulbright program, and they got a many different type of opportunities for young postgraduate students, for postdocs, for young faculties, even for senior faculties, and so on. So I'm one of the Fulbright alumni, and also in the selection panel committee by appointed by the what do you call like a government of US. So if you need to find more details, you can always can contact me. And second is I also want to share with you Global Young Academy. So your academy need to appointed you or need to nominate you. This Global Young Academy, the date I put is 21, but every September it will be open. And those who are below 40 years old, you can apply for this Global Young Academy. And under this, you got a lot of opportunities like a networking, like I got a grant, exchange program, like an attachment, internship, so on. So please go and look into this website as well. And this Global Academy is the headquarters is in Germany. Next is the World Academy of Sciences. Like Malaysia, we come under Beijing Chinese Academy of Sciences, and Indian researchers will come under Bangalore. So TWAS also got many opportunities. If you go to the website, they got like about network and opportunities. So under opportunities, you can see there is a many kind of postdoc opportunities attachment. So for example, just say you wanted to come and attach to work in our lab in University of Malaya, Malaysia, you can apply the postdoc fellowship or any other fellowship under this to us. So since I can be the host, the funding will come from the to us, and you can come for an attachment to work in our lab. Next is ASEAN India Science Technology Innovation. So I had 3 grants previously. One is ongoing. So with the Banaras Indian University, Teshpur University, and also with the VIT. So this is another good platform where we can work together in some projects where the money will be parked under India. You need like 2 partners from 2 different ASEAN countries. So this is another good opportunities for Indian researchers to work on it. So hopefully, if you got any idea, we can work on this approach as well. And then Erasmus funding. So this another international funding where they give millions of money, and this is focusing on the international research as well as capacity building for higher education institute. And if you look that India is one of the country involved here as well. So if you got any opportunities, you want to work with us, please contact me. I can guide you and we can put a proposal together as well. Next, at University of Malaya, we also got like a University of Malaya Excellent PhD Scholarship. So please check University of Malaya website. If there's a call for PhD scholarship and also for the postdoc scholarship, please do contact us so we can guide you on these kind of applications. Okay, last but not least, if you want to go fast, go alone. If you want to go far, go together. So this kind of networking and this kind of collaboration is very important for all of us to go far together. So final gratitude to my family, to all my teachers from my primary school until now, to all my students and collaborators. Without them, I'm not possible to present any of my research work here. University of Malaya, my friends, and also taxpayers, because they are the one who are paying our salary and our funding and everything. And again, thank you very much for the organizers, and a special thank you for Dr. Prasanth Kumar for connecting me with your esteemed institution. Thank you all.
Any questions from the audience? Online?
Okay, I think there is one question here. Sir, can magazine synthesized by chemical methods? Okay, there is one question here. So actually, the magazine, yes, we can do with the chemical methods. I'm in a conference talk.
No questions? Okay. I thank you for the excellent session and for sharing your insights on the topic, sir. Thank you very much, sir.
There is one question in the chat box here. Can I answer for that?
Yes, sir.
Okay, the question is about the magazine synthesized by chemical methods or not. It is possible. So it depends what type of magazine we needed to prepare, whether it's a carbide base or nitrate base. Then from there, we have to get the appropriate chemicals. Then by using like a max phase, from there we can get the magazine. It is a chemical method. If you want a very specific methodology for any specific method, you can always email to me. Then we can guide you on preparing the magazine. It is a quite a simple method, not a difficult one. I shared my email address in the chat box. You can always contact me.
Okay, thank you, sir.
Thank you, sir, for sharing the insights about the advanced material characterization techniques and their utilization in renewable energy. I also thank Dr. M. Lawrence for chairing the session.
Professor, good afternoon.
Good afternoon, Professor.
Okay. Shall we start the session?
Yeah.
Just a minute, sir.
Every crystal holds a secret of the universe. I now invite Dr. P. Kristuraj, Associate Professor of Physics, to chair the session on crystal growth structural SHG nonlinear optical analysis DFT studies on 2-methyl imazodium succinate single crystal by Professor Dr. Stephen Raj A., Research Scientist, Rhodes University, South Africa. Over to you, sir.
Okay. Thank you for nice introduction.
Just a minute.
Am I audible?
You are audible, sir. Just a minute.
Okay.
Dear students, good afternoon to everybody. It's my immense pleasure to introduce today's speaker, Professor Dr. Stephen Raj, Research Scientist, Rhodes University, South Africa. He did his UG in AVC College, Bharadas University, Mailadurai, PG in Pumbagar College, MPhil in St. Joseph's College in our campus. He is a proud alumnus of our college department and did his PhD in SSN Research Center, Anna University, Chennai. So he worked as an assistant professor in St. Joseph's Arts and Science College, Madras University, and also in Muhammad Sadiq AJ College of Engineering. So he received many awards and prizes as Best Teacher Award in the academic year 2022-23 at Muhammad Sadiq AJ College of Engineering, and he also got Best Poster Award for the paper titled Synthesis and Characterization of Tin Oxide Thin Film Nanoparticles. See, he has published more number of journals in the revered journals, and he also give He has also served as an invited speaker in the National Conference on New Horizons in Applied Research for Sustainability in the University Reva during the year December 2024. So he have presenting many papers in various conferences. And on behalf of our department and our college, I am wholeheartedly welcome the Professor Dr. Stephen Raj, and he is going to give a lecture on crystal growth, structural, second harmonic generation, non-linear optical analysis and DFT studies of 2-methylene succinate single crystal. So I welcome you, sir.
Thank you. Thank you for nice introduction, sir.
So over to you, sir.
Sir, am I audible, sir?
Yes, sir. Yes, sir.
Okay. The screen visible, sir?
Yes, sir. It is visible.
Okay. Good afternoon, everyone. It is an absolute honor to be here today at the International Conference on Advanced Materials. I would like to thank the organizers for inviting me to speak and for their efforts in putting together such an incredible platform for sharing ideas and advancing our field. My name is Dr. A. Stephen Raj from Department of Physics and Electronics at Rhodes University in South Africa, and I specialize in crystal growth and density function theory. I am currently working on the role of point defects of thermoluminescence, optical stimulated luminescence of dosimetry, and density function theory. Today, I will be talking about experimental and a computation of high quality of nonlinear optical single crystals for second and third harmonic generations applications. The outline as follows: introduction, growth of single crystals, development of crystal growth technology, growth of NLO crystals, slow evaporation solution technique grown crystals, growth of imidazole derivative single crystals by slow evaporation solution technique, experimental technique, density function theory, comparative characterization, experimental and density function theory, and final conclusion. Introduction. Why crystal growth? For thousands of years, people have been fascinated by crystals. Engineers have been drawn to crystal for at least 50 years since they are essential components of optoelectronics, electronics, and other technical fields of application. The development of information technology has brought the concept of the global village into reality. One of the materials that meet the demands of the current communication sector is crystal. The growing interest in the crystal formation process has been observed during the last few decades, especially in light of the rising need for materials for technological applications. Normally, we know that matter exists in three states: solids, liquids, and gases. In the solid state, a material can be subclassified as crystalline, amorphous, and quasi-crystalline. An organism, aggregations of the component atoms, molecules, or ions in three-dimensional periodic arrays lead to the formation of the crystalline state. The crystal symmetry in arrangement, molecular structure, orientation, and the physical-chemical environment of their formation give rise to the distinctive direction, dependent physical properties, and other chemical feature of crystals. The macro, micro, and nanocrystals are the different size of crystals. The macro crystals are organized millimeter size of crystals, for example, 10-3 meter and larger in size of crystals. They are clear crystals that can be seen in quantity. The microcrystals are crystals that are very tiny. And also the nanocrystals are defined as having a dimensions with order of, for example, 1 to 100 nanometer. The recent development and advancement in the field of semiconductor transistors, solid state lasers, ultrasonic amplifiers, non-linear optics, infrared detectors, piezoelectric, thin film, photosensitive materials, and the computer industries can be attributed to the significant influence of single crystals in modern technology. Due to the availability of single crystals like silicon, germanium, and gallium arsenide, as well as the discovery of non-linear optical characteristics in some inorganic, semi-organic, and organic crystals, all these discoveries were possible. Only some single crystals display the desired physical phenomena for the manufacture of devices. The high quality of single crystals are required to achieve the excellent performance. Growth of single crystals. Alchemy may be seen as extending into attempts to grow single crystals with high values like jewels in a lab utilizing less expensive and easily accessible basic materials. In the middle of the 19th century, the first success in growing gemstones was achieved. High temperature solutions have been used to grow emerald crystals up to 1 carat in size of single crystals before Bernoulli discovery, which allowed for the growth of massive ruby crystals. From the melt phase, attempts to generate big single crystals of ruby from high temperature solutions were unsuccessful. The creation of huge single crystals was needed in many scientific and industrial areas. The contributions of crystal growth research led to the significant development of various industrial fields in turn. A good example, metrology. The piezoelectric and optical single crystals are some of the examples to use these crystals in electric and optical communications technology. Very large single crystals, at least several centimeters in diameter, must be grown. For that reason, solution growth techniques were originally used to grow massive single crystals such as ammonium dihydrogen phosphate and potassium dihydrogen phosphate for piezoelectric applications. Why crystal growth process? The crystal growth process is important because it allows for the creations of crystals with ideal properties by regulating external factors. The process of crystal growth is driven by supersaturation or supercooling. Why reason for growing single crystals? The growing single crystals is critical for various scientific, industrial, and technological applications due to the particular structural and physical properties. The single crystals like silicon, gallium arsenide, or sapphire are indispensable in the semiconductor industry for microchips and light emitting diodes. What is the importance of crystal growth? In the modern day, single crystals have been effectively applied in several fields. The electronics industry and the systems it supports have undergone significant changes as a result of the symmetry, purity, and simplicity of single crystals. What is the crystallization process? The crystallization process is a natural or artificial method of forming solid crystals from a homogeneous phase such as a solution, melt, or vapor. Optimizing growth parameters. The first one, purification of the materials. A high degree of materials purity is a requirement for crystal formation. As a result, the material must be purified using the proper solvents before crystal formation can begin. Repeated crystallization of the materials in inappropriate solvent can lead to purification. Crystallization and solution preparations. The material solubility information at various temperatures is crucial for solution formulation. The solution filtering employs sintered glass fibers with various pore diameters. Seed preparations. The seed preparations of the quality of the seed crystal utilized has a significant impact on the quality of the developed crystal. In the label area of the supersaturated fluid, spontaneous nucleation can produce small seed crystal. Crystal habit. The amount of supersaturation must be maintained uniformly across the surface of the growing crystal in order to have a regular and even growth. Agitation. The agitation of the amount of supersaturation, most of the time, all crystals developing can be maintained uniformly across the surface of the growing crystals and regular and even the growth. Cooling rate. The cooling rate of the growth solutions temperature is decreased in order to achieve the necessary of the supersaturation, which is what propels crystals formation. The programming should be done to match the cooling rate to the crystal growing rate. Crystalline perfection. The crystalline perfection based on the grown crystal's perfection, such as purity of the starting material, cooling rate employed, quality of the seed crystals, and the efficiency of agitation. Development of crystal growth technology. The technology for solid state devices and research are based on new materials with the invention of a flame fusion growth technique by Bernoulli in 1902. The industrial manufacture of crystal began. He can be recorded as the founder of crystal growth technology because most followed melt-based growth methods like Chiropoulos, Sokratski, Bridgman, Taman, Stober, Stockberger, etc. The concepts are used for controlling crystals, nucleations, and diameter. As a technology advanced in the 20th century, crystal growth technology and epitaxy technology also advanced. On the other hand, an astonishing success in the creation of huge, very perfect crystals and large diameter epitaxial layers has made it possible for the rapid advancement in communication technologies, microelectronics, energy, medical instruments, and space technology. Crystal growth technique. The crystal growth methods various type of such as growth from solid, growth from vapor, growth from melt, and growth from solution. We have focusing the growth from solutions such as slow evaporation, slow cooling, temperature gradient, gel growth. The solution growth method, there are two types of method. The first one, low temperature solution growth and high temperature solution growth. We have focusing the low temperature solution growth has been classified into the following methods such as a slow evaporation method, slow cooling method, and a temperature gradient method. Slow evaporation technique. Here, the most popular solvent is water. The saturated solution is created by combining the right solvent with the initial components and dissolving them. Through the gradual evaporations and consistent temperature, it reaches the supersaturation point. A perforated lid is placed on top of the finely prepared saturated solution before being transferred to a dust-free clean container. This technique includes stabilizing the temperature to around 0.005 degrees Celsius. and evaporating at rates of a few cc per hour. The method drawback the protection of undecided nuclei as a result of the solvent evaporating of the solution surface. This nuclei produces small crystals which dissolve in the solutions and obstruct crystal development. Compared to gradual cooling, this approach produces crystal of a larger size of crystal, and although the quality of the crystal may be impacted by the changing rate of evaporation. Uh, Despite of all these drawbacks, this is a practical and simple approach for generating large, high-quality single crystals. The only way to produce organic crystals with low melting point, quick decomposition rate, and low temperature coefficients of stability is by this technique. Slow evaporation solution technique, some advantages and some disadvantages. The advantages such as a simple and low cost setup, low temperature, no need for drying and annealing, minimum environmental impact, no need for other agents, high quality of single crystals, X-ray diffraction analysis, and determinations of atomic structure was confirmed for NLO materials, and other some disadvantages, solvent inclusions, low crystal growth, some cases of materials, compound decomposition, environmental impact, poor diffraction, some cases of materials. Non-linear optical crystals. Classification of NLO materials such as organic, inorganic, semi-organic. We have first the focus inorganic. The bulk inorganic materials make up the first significant classes of materials. These materials, non-linearities are caused by electrons like those in metals and semiconductors that are not connected to specific nuclei. The best non-linear materials are inorganic crystals like KDP, ADP, and KTP that are increasingly used in electro-optical applications as well as a second harmonic generation. The most popular crystals for second harmonic generation is potassium dihydrogen phosphate, which has a broad transparency range, good birefringence, and a modest optical damage density. After numerous attempts, excellent non-linear boratic crystals with a wide range of transparency have been found. And other organic crystals. There are number of ideas that can help in designing organic molecules with a significant optical nonlinearity. Second harmonic generation is a second order nonlinearity process that is impacted by crystalline arrangement and molecular structure in crystals. Demonstrate that extended conjugations under the presence of a low laying spectroscopic charge transfer resulting from electron donating and electron accepting substituents and aromatic ring or related conjugated system increases second order nonlinearities in organic compounds. Even so, the majority of organic compounds, 70% fail to show second harmonic generation's activity because they crystallize in centrosymmetric space group with inversion symmetry. Given this circumstance, a number of methods for producing acentric crystals capable of showing SHG have been suggested, such as the first one, chirality, electron polling, hydrogen bonding, channel inclusion alignment, dipole to dipole interaction, lambda type of molecules, and co-crystallization. Semi-organic. The semi-organic material in generally second order nonlinear optical efficiency is very high in organic materials. However, the mechanical and thermal stability of majority of organic nonlinear optical materials is poor. When inorganic compounds are introduced to organic compounds, the inorganic compounds mechanical strength and thermal stability are interest. Semi-organic materials are currently used in substitute of inorganic and organic components. This is a result of the improvement in second harmonic generation's efficiency and mechanical and thermal stability. The semi-organics are the name of this new course of materials. Organic nonlinear optical materials benefits, such as they have substantial nonlinear merit figures, high optical damage threshold, they demonstrate quick reaction time, they are easily obtainable as liquid crystal fibers and ultra thin film. Their adaptable architectural design makes it simple to control attributes across to a broad spectrum. Properties needed for nonlinear optical crystals, such as high NLO coefficient, high laser damage threshold, fast optical response time, wide transparency range, high thermal, mechanical, and chemical stability, and easy devices fabrication was confirmed for NLO materials. Slow operation solution technique ground crystal. We have choose the one of the crystals for slow operation solution technique. The 2-methyl-imidazole and succinic acid were efficiently dissolved in the solvent of deionized water. In the equal molar ratio 1:1 at room temperature, the mixture was continuously stirred in until it became a homogeneous solution. The solution, which was filtered through Wadman filter paper, was taken separately in a beaker. Moreover, the beaker was tightly covered with polythene sheet wherein tiny holes were made so as to ensure crystallization by solvent evaporation. And the growth system was kept in a dust-free ambience that was maintained at the controlled room temperature in order to ensure slow evaporations of the solvent. After a few days, white-colored 2MISA crystals were successfully grown, and the grown crystals were allowed to undergo recrystallization process in order to remove the impurities present, such that this process would improve the optical quality of single crystals. Slow operation solution technique grown imidazole derivatives crystals for NLO application, such as imidazole L-tartaric acid, 2-ethyl-imidazole D-tartaric acid, 2-methyl-imidazole succinic acid, 2-methyl-imidazole oxalic acid, imidazole succinic acid, 2-methyl-imidazole D-tartaric acid. This materials was published. Experimental technique. NLO technique, there are two types, the Kurtz powder SKG method and Z-scan technique. The Kurtz powder SKG method, a powder SKG approach was put forth by Kurtz and Perry 1968 for a through examination of the second order nonlinearity. The Kurtz 1968 used this method to examine a large variety of chemicals for their nonlinear optical characteristics. The output of the NDYAG ray laser is called neodymium doped yttrium aluminum carbonate, can be used to investigate the sample's nonlinear optical behavior as it passes through the crystalline powder. About 6 millijoule pulse of fundamental radiations at 1064 nanometer were produced using a Q-switch mode locked NDYAG laser. There are two ways to use this laser. The laser produces single 8 numbers pulse while operating in a single shot mode. The laser generated a continuous train of 8 numbers pulses at a repetition rate of 10 Hz while operating in the multi-shot mode. A single shot mode of 8 numbers laser pulse with a spot beam of 1 millimeter has been used in the current work. A mirror and a 50 per 50 beam splitter are used in this experimental setup to produce a beam with a pulse energy of approximately 6 millijoule. The amount of light that the sample emitted was measured using a photodiode detector and oscilloscope combination. The emission of green radiation 532 nanometer and the optical signals collections by photomultiplier tube. In a comparable capillary tube sealed at one end, microcrystalline powder of urea or KDP was taken for comparison. We compared the sample's second harmonic output intensity to that of either KDP or urea. And another Z-scan technique. The nonlinear index of refraction and the nonlinear absorption coefficient are the two nonlinear interactions that can be calculated in this way. The sample is located at a position is at the reference detector is a D1, the prop detector is a D2, and the beam splitter is designated as beam splitter. As it moved along the Z-axis, a sample that exhibits nonlinear refractions can function as a lens with a changeable focal length. In these experiments, it may be preferable to use these materials with negative nonlinear indexes of refraction and thickness below the diffraction length, also known as the Rayleigh length of the focused laser beam. As a result, the aperture in front of the detector has a smaller spot size, resulting the better transmittance through the aperture. Due to this intensity, this impact gets stronger as the sample gets closer to the focus. The sample can transmit the lightest through the aperture when it is just in front of the focus. As the sample is moved further and the beam diverges due to this sample negative lensing, the maximum transmittance of a peak will decreases to a minimum of transmit of the valley. In this case, the nonlinear refractions and nonlinear absorptions are not factors affecting the measured transmittance. The plotting the data from a Z-scan without the aperture results in a valley that is symmetrical to the focus. The nonlinear absorptions coefficient is calculated using open aperture Z-scan. Second harmonic generations of NLO measured, such as rapid characterization, time and resources efficiency, laser frequency doubling, optical signal processing, and estimating effective nonlinear susceptibility was confirmed for NLO materials. The Z-scan of NLO measured, such as nonlinear refractive index, nonlinear absorption coefficient, nonlinear index nonlinearity, and metabolic activities, was confirmed Z-scan for NLO materials. Comparative characterizations of 2-MIO experimental and density functional theory. We have focusing of 2-methylimidazole oxalic acid with the experimental characterizations such as sum of characterizations, single crystal X-ray diffraction, powder X-ray diffraction, U visible NIR analysis, thermogravimetric and differential thermal analysis, SKTG analysis, and Z-scan technique. Single crystal and powder X-ray diffraction analysis. The obtained lattice parameters of 2-methylimidazole oxalic acid was confirmed crystal structure monoclinic with a space group P21. The powder XRD analysis. The powder XRD of a sample can provide useful information about a sample such as phase identification, sample purity, H-scale planes, and morphology. The broadening in the peaks of the XRD pattern arises due to the finite size of the crystal. If one of the crystals of infinite size, the peaks in the XRD pattern will appear as very sharp and size get reduced peak of the broadening 200 of peak. UV visible NIR analysis. The optical transmittance was investigated for the 2MIO crystal using the UV visible NIR spectral analysis, which would confer the factors such as region of optical transmittance under the lower cutoff wavelength. Generally, efficient nonlinear optical materials to possess the cutoff wavelength less than 300 nanometer, such that a wide region of optical transparency is also required. The analysis of optical transmittance of the 2MIO crystals to 1.5 millimeter thickness was undertaken, making use the recorded U visible NIR transmittance spectra as shown in this figure. Interestingly, the 2MIO crystal displays an output of a low cutoff wavelength 280 nanometer, which is due to the pi to pi transition, such that an excellent optical transmittance of nearly 80% within the U visible NIR region is obtained, and hence it can be utilized for the applications of optoelectronic devices. As per the top plot drawn, the optical bandgap energy was obtained by extrapolating the linear plots alpha HB and HB shown in figure, whereby the bandgap energy was evaluated to be 4.30 electron volt because of the exceedance of wide bandgap, high laser damage threshold, and larger transmittance region. The crystal is a good fit for the application of optoelectronic devices. TGDTA analysis. The DTA plot curve suggests that the 2MIO compound has an excellent crystallinity as well as purity. The mass change concerning the temperature range of 60 degrees Celsius is evident, such that there are no water molecules present, which was used as a solvent while crystallization was in progress, as found in DTA. From DTA, materials weight losses start 60 degrees Celsius, while the decomposition temperature is 161 degrees Celsius, which indicates the process of gradual weight losses for the sample. Furthermore, the dissociation temperature of the material of the 234 degrees Celsius, at which there is a heavy weight losses of the sample, and it happens for the sample because of the process of a simultaneous melting and dissociation point, temperature is reached. Also, the TG show that the minor weight losses starts at the temperature range 61 degrees Celsius to 179 degrees Celsius, and the major weight losses occurs to 46 degrees Celsius. SKG analysis. When the sample powder of crystal was confirmed with a laser source of green light emissions in the SKG signal was determined from the sample, the observed SKG efficiency of 2MIO and KDP crystals are 45 millivolt and 75 millivolt respectively. We have get the SKG efficiency of 2MIO crystal was found to be 60% that of the comparing KDP crystals. Z-scan technique. The third order nonlinear optical characteristics of 2MIO were undertaken by performing the Z-scan measurement The approach facilitates for a simultaneous measurement of magnitude as well as a sign of the nonlinear absorption coefficient and a nonlinear refractive index. The transcendence closed aperture Z-scan spectrum of 2 MIO single crystal is show the figure, and it is show reverse saturation absorption from the closed aperture Z-scan of 2 MIO single crystal. The measurement of the peak was performed, which is shown in figure. The upward transmittance of peak value is 0.028 and downward directions transmittance value 0.0228 with the corresponding same values. Finally, the parameters other properties was measure value such as confirmed for NLO materials, nonlinear refractive index value is 1.08 into 10 power minus 12 meters per watt. Nonlinear absorption coefficient value is 3.06 milli per watt. Density functional theory. What is the density functional theory? The density functional theory is a quantum mechanical modeling method used to investigate the electronic structure, ground state properties of many body systems, particularly atoms, molecules, and condensed matters. What is a DFT used for? The DFT is a versatile computational methods widely used to study the electronic structure of matter. Its applications span multiple scientific and engineering fields due to its ability to provide accurate results while being computationally efficient. What is the purpose of DFT? The purpose of DFT is to determine the electronic structure of many body systems such as atoms, molecules, and solids in a computationally efficient and accurate way. What is the importance of the DFT? The DFT is one of the most important and widely used tools in quantum mechanics, computational physics, chemistry, and material science. Its importance lies in its ability to provide a detailed understanding of the electronic structure of many body systems while balancing computational efficiency and accuracy. Different bases of set for DFT. The bare minimum number of basis function required for each atom is contained in minimal basis set. The bare minimum basis set is STO3G is called Slater type orbitals. 3 Gaussian primitives per basis functions are denoted by 3G. By increasing the number of basis functions per atom, the basis set can be expanded. For each valence orbital, split valence basis sets like 3-21G have 2 sizes of basis function. Popol's split valence double theta basis set known as 6-31G has a core orbital consisting of CGTO is called composed of 6 Gaussians and 2 orbitals that describe the valence. A CGTO composed of 3 Gaussians and a single Gaussian. For each type of orbital, 3 sizes of contractor functions are used in triple split valence basis sets like 6-311G. One can only alter the size of split valences basis set. The shape can't be altered. Diffuse S and B orbitals functions for atoms other than hydrogens are added 6-31 plus G and 6-31 plus G also has a diffuse function for hydrogen. Gaussian.
Sir, excuse me,
It
sir.
represents,
Can you wind up in
sir,
5 minutes, sir? Can you conclude it?
sir, how long, sir? 5 minutes.
Yes, sir. Maybe you can take around 10 minutes also.
Oh, okay, okay, okay. Graphical user interface for Gaussian 09W. The various outcomes Gaussian calculations can be graphically Gaussian view, including atomic charges, molecular orbitals, density and other properties, vibrational frequencies, the geometry optimizations, and the potential energy surface. Applications of DFT. The first stage of any DFT analysis is to perform molecular structure optimizations, and crystallographic parameters are hypothetically modeled and then perform measurement to confirm that the molecule configuration is stable, that is, its energy is minimum, such as vibration spectral properties, homolume analysis, natural bond orbital analysis, dipole moment, and polar stability. Some of DFT characterizations such as optimized molecular geometry, homolume analysis, Mulliken atomic charge analysis, natural bond orbital analysis, and hyperpolar stability studies. The optimized molecular geometry. The optimized molecular structure and numbering of the atoms and the compared DFT, optimized molecular geometry, and the single crystal XRD patterns such as bond length and bond angles. The molecular strong interactions between DFT and XRD were determined in the gaseous state. Both the methods are of good consent with each other, such that they give results with X-ray diffractions and theoretical geometric parameters. Homolume analysis. The electrical and optical properties are significantly influenced by HOMO as a quick bath of kinetic stability. The energy gap between the highest occupied molecular orbital is called HOMO, and the lowest unoccupied molecular orbital is called LUMO, has been utilized. A molecular that has a less energy gap, HOMO and LUMO, is more polarizable. Hence, the ionization potential would be directly related to the proposed HOMO and energy, and LUMO energy can be accepted as a consequence of electrons, and LUMO energy is a direct contribution due to the electron affinity. So the highest energy value is minus 5.63 electron volt, and lowest energy value is minus 1.1006 electron volt, and the final to get the band gap energy value is 4.53 electron volt. Mulliken atom charge analysis. The negative and positive energy values of the carbon and oxygens, high negative charge values indicated with hydrogen bond is a highly positive energy values. Natural bond orbital analysis. The natural bond orbital analysis was undertaken for all bonding orbital interactions occurring between filled leaves type is called donor, and empty non-leaves type is called acceptor of natural bond orbitals, such that the stabilization energies U2 were determined by the second order perturbation theory. The orbital bonding interactions would lead to the formation of donor is called occupancy, and acceptor is called occupancy orbital, and final stabilization energy U2 relevant to the delocalizations I and J is obtained. Finally, it is noted this leads to hydrogen, its very strong stabilization energy values 54.34 and 46.58 calorie per mole respectively. Hyperpolar stability. The NLO properties such as large dipole moment, linear polar stability, hyperpolar stability, and anisotropy values are determined for 2 MIO crystal by computed by using DFT B3LYP -6-311G DP is called density function theory Beck 3 Lee Young pair of ground state. It is commonly recognized that the sublime first order hyperpolarizability beta tiny laying ground and excited state which a change dipole moment of transition. The computed values of the dipole moment, polarizability, anisotropy, and first order hyperpolarizability for the 2 MIO compound were found to be 8.26 dB and alpha minus 1.03 10 per minus 23 ESE values and beta total 1.85 into 10 per minus 30 ESU. The computed first order hyperpolarizability value for 2 MIO is 4.95 times more than the standard urea crystal. The 2 MIO compound NLO properties was confirmed the NLO crystal. Conclusions. In conclusions, the imidazole derivative crystals growth characteristics and advantages physicochemical characteristics such as the higher esthetic efficiency, third order harmonic generation, thermal stability, good transparency and wide bandgap suggest that there might be promising materials for use in the fabrication of optical switching, photonic, nonlinear and optoelectronic devices. Thank you. Thank you for giving an opportunity, Dr. Johnson sir and other faculties.
Thank you, Dr. Stephen, for your wonderful talk about this crystal growth. Dear student, this is the time for asking some questions based on the basic crystal growth techniques and what you have learned from his talk. Anybody?
Sir, I have one question.
Yeah.
Sir, your session was interesting. You have mentioned that one 2-methyl-imidazole based derivative crystal shows 60% that of standard KDP, which means only 0.6 times. Only 0.6 times that of KDP. 60%. Is it so?
No, but that one only converted percentage.
Okay. How many times
Yeah,
to that of KDP?
4.95 times.
Okay.
Yeah.
Yes, sir. And nowadays, a huge number of articles in crystal growth has been published, but they show less efficiency compared to the standard KDP or urea. So what is the significance of those articles, sir?
Yes, urea is good good for NLO crystals. So we have choose the comparing any one materials with the comparing urea for NLO materials because that one crystals is a purity crystals.
There is an online question, sir.
Sir, some of the questions can be asked through online. So what about the second order polarizability of the imidazole crystals? Asked by Diana.
What is the second order? Sorry. Again,
What about the second order polarizability of the imidazole crystals?
Okay. Yeah, that one. Yeah, this
It is measured by DFT.
We have. Yeah, this one of the NLO properties is called the dipole moment polarizability and first order hyperpolarizability. So this confirmed for NLO materials.
Any other
Yes,
questions
sir.
from the audience? Yes.
Good afternoon, sir. Good afternoon,
Good
sir.
afternoon. Good afternoon. Good
I'm
afternoon, ma'am.
Kavita from first MSc Physics. Can you give the
Okay,
clarity
ma'am.
about the band gap of crystals so that we can use that for optical applications?
Okay. Yeah, this one. Can you ask this one?
Once again, repeat the question.
Band gap of
Can,
crystals for using in optical applications, sir.
yeah, the UV visible NIR analysis, the confirmed optical transmittance for band gap energy values. For example, um, starting 4 point up to maximum 5.8 band gap energy we have get the from materials, so it's a confirmed for NLO materials. And also cutoff wavelength, so less than 300 nanometer. So this material confirmed 280 nanometers, so was confirmed for NLO materials.
Thank you, sir.
Any other questions, dear students? Hope you everyone can understand the basic principles of the crystal growth and the various techniques involved in growing a single crystals. Thank you, Dr. Stephen, for your wonderful talk in this session. Thank you once
Thank
again.
you, sir. Thank you so much.
Thank you, sir.
Thank you.
Thank you, sir, for a wonderful session. I also thank Dr. Kristuraj for chairing this section.
So thank you, sir. Participants, we will call off for lunch today. The lunch is served at the physics laboratory. You can go to the department and have a good lunch, and we'll be back at 1:45 sharp. Okay? Take your time in eating.
Dear
Please
student, please wait.
come back at
I
1:45.
request all first MSc and second MSc students of shift 1 and shift 2 to assemble here at 1:45. Also third UG, the attendance will be taken by the class in charge.
1:45 sharp. Thank you.
Once again, the first PG, second PG and third UG of shift 1 and shift 2 students assemble here at 1:45. The attendance will be taken by the class in charge. Thank you.
Let me, I am invited speaker. Invited speaker. Research person. Yeah, international conference. Yeah, it is first time.
Good afternoon. Is it my voice is clear?
Yes, sir, it is audible.
Okay, it is audible, right? Like, can you please allow me to share screen, whether it can be coming in or not, please?
Yes, sir, yes, sir.
Can you try now?
Yes, sir, you can share.
Yeah, I'm trying now. See. Is it the screen visible?
No, sir.
Yes, sir. It's visible.
Let's say if I play a video, could you please check whether the sounds is coming up?
Yeah, it's playing with the song.
We learned from the past.
Playing with the song.
It's all coming, right? All
Yes,
sounds.
it's.
Okay, then fine. I'm ready then anytime.
I will be starting in a minute, sir. Yes, sir.
Sure, sure.
Yes.
May I know the time, how much time I'm using?
Probably the time is 1:50 here. 1:50.
No, because initially it is given by Prof. Johnson is 1:45 to 2:30. Okay, now I understand that we are starting late. I mean, is it 45 minutes, the total duration?
Yes, sir.
Or is it like only 45 minutes for presentation plus Q&A so that I can plan accordingly?
It's with the Q&A, sir. We are probably planning for with Q&A. Is it okay?
I mean, including Q&A is 45 minutes.
Yes, sir.
Okay, so that means I can finish by maybe 40 minutes at least.
Yes, sir.
So, okay. So if we start at 2 o'clock Indian time, maybe I can go up to 2:40.
We'll be starting in a minute, sir. Just we are making some changes, that's all.
Okay.
Yes. We can go, sir. Yes, sir.
Anand, welcome. Anand.
Good afternoon, sir.
Welcome.
Good afternoon. நல்லா இருக்கும் sir. Thank you.
Okay. Proceed. Okay. Thank you. Good afternoon.
Good afternoon, everyone. It is my great pleasure to introduce Professor Dr. T. Joseph Sahaya Anand, Faculty of Manufacturing Engineering, University Technical, Malaysia, who will be our esteemed resource person for today's session. He has completed his postgraduate at St. Joseph's College in 1997. He is our alumnus. It's a great pride for us. He has completed his MPhil at BDU in 1999, followed by PhD in the field of Material Science from University of Hong Kong in the year 2004. He has held several important positions during his career, including Junior Research Fellow at Department of Physics, Alhappa University, Karaikudi, Postdoctoral Fellow at Japan, Senior Lecturer and Associate Professor at Malaysia, and he is a freelance trainer at Malaysia. His research focuses on green technology, mobile technology, smart materials, smart vehicle, biomedical engineering. He is having research collaborations with University of Hong Kong, Japan, and Bharatiyar University, India. He has published 11 books, 88 papers in international and national journals, and attended 67 international and national conferences, and received 10 international and national awards. He is having 1,941 citations in Google Scholar H-Index and 20 in Web of Science H-Index. And he is a trainer provider in Lean Six Sigma. He is familiar in framing the syllabus for diploma, degree, and master, and its benchmarking. He recognizes many scientific conferences at international level, both in regular and virtual mode. We are fortunate to have such kind of resource personality. Professor going to deliver a talk on the mystery of transition metal chalcogenides and intermetallic materials. Let's refresh our knowledge in this field. I welcome you, sir, for this session. Welcome, sir.
Thank you.
Over to Professor.
I hope my voice is clear now.
Yes, sir. It's audible.
Okay, சபையோர் அனைவருக்கும் இனிய மாலை வணக்கம். So without further ado, I can directly go because the time given to me is only 40 minutes. And before I go into the session, I will share about like what is my prime focus today. I'm not going to talk about detailed research or any particular one today, because understanding that the participants today, including students and scholars, not only researchers completely. So I'll be choosing to share on that's why even in the title I use the word mystery of intermetallic compounds and transition metal chalcogenides. So what it is, etc. So before that, as a courtesy, I would like to introduce about my university with the corporate video that we normally do that. So please allow me to share on that. I hope the screen can be seen and the volume is coming
Yes, sir.
up.
It's good.
Please, thank you.
We learned from the past, but what we sow now is what we will be reaping in the future. Malacca, a historical city, once in melting pot of many civilizations that attracted the mind of the Portuguese, the Dutch, the British, and the Japanese to take control, is now adding another jewel in the crown. UTAM, a place for world-class engineering for the future. A university with the basic aim to train its students to take on the world with the necessary knowledge and tools to build the future, to improve human life through technology. It is about creating engineering for the future. UTAM is an advanced engineering environment. We call it Advanced Manufacturing Technology or AMT. There are 4 thrusts underpinned in the AMT. Green Technology, Systems Engineering, Human Technology Interaction, Emerging Technology. Each and every thrust is interlinked to facilitate and commercialize research products and at the same time help to fund the latest technology. Green technology is the application of engineering, technology, and management to conserve the natural environment and resources. Systems engineering is the field of engineering and technology that focuses on how complex engineering projects should be designed and managed. Human Technology Interaction (HTI) is the study of interaction between people and technology. Emerging technology brings about new territory in some significant ways in their field. With the four trusts underpinned in UTAM, it will help to synergize all the faculties on where they should be heading. Most machinery requires a lot of attention and very hard to monitor because of the lack of workers. Manufacturing operations use a lot of electricity, which contributes to the greenhouse effect. To strive forward, effective communication is a very important part in any organization today. All the information that is stored in the server is prone to virus attacks. With great technology, there will be a great need to market the technology for everyday use. What good is there if the future engineers cannot communicate their ideas effectively? UTAM pledges to strive for continuous innovation in research projects and programs that benefit all. The highly specialized academic programs at UTAM is industry-driven and market-relevant. UTAM.
Okay, so thanks for watching our university corporate video. So that gives us information about our university. Okay, coming back to today's topic. So I said the first one will be intermetallic compounds. And the word intermetallic gives a specific name. If we just normally look into what is intermetallic, it is nothing but a material or a system which is in between. In between, it can be from a hard metal to light metal. It can be from a metal to insulator. So a property which normally in between, we can call intermetallic. That is one way. On the other hand, we also call it as when two or more materials put together, we also call it as intermetallic. Then the question comes in. When I am combining or when I am melting together or when I am, diffusing together two materials, normally we call it as compound, alloy. Then what's so special about this particular word, intermetallic compounds? So to answer that, intermetallic is two or more metallic elements with optionally either one could be either metal or another could be a non-metal. But the most important thing here, the properties of a new material become either higher than the highest or lower than the lowest. Okay, I can give one example. Nickel is one metal. We all know that nickel is a hard metal. Aluminium is also another metal which categorized as a light metal. So I have a hard metal, I have a light metal. So to give little bit more on quantitative information, the melting temperature of nickel is normally 1230 degrees centigrade, 1230 degrees centigrade. When it comes to the aluminium, which has the melting temperature of 660 temperature, 660 degrees centigrade. So if I am combining these two, nickel is, let's say, put it very simple, I am not going into atomic percentage, weight percentage, etc. I am taking a one piece of aluminium, one piece of nickel, and I want to merge it together, either by casting or welding. There are many methods. So here normally we use casting. So completely we merge it together, going up to its melting temperature to make it an alloy. And that still I can call that alloy an intermetallic compound because just now, if you remember, I said nickel has the melting temperature of 1230 degrees centigrade, aluminium has 660. When I am combining together, now it is become nickel aluminum alloy, NiAl alloy. So this alloy normally have the melting temperature of, that is our expectation, mathematically what we call 1230 plus 660, 1990, nearly 2000 degrees centigrade. The resultant material, which I can call it as nickel aluminum alloy, should have the melting temperature of 1000 degrees centigrade or exactly 995. This is the simple mathematical expectation. Normally, most of the times it happens, so we call it as an alloy. But surprisingly, this particular compound, intermetallics, the new material which is nickel aluminide or nickel aluminum intermetallic compound, has the melting temperature of 1570 degrees centigrade. 1570, which is higher than even nickel. See, the raw material nickel has the melting temperature only 1230. The another one is of course only 660. So when I am combining these two, at the maximum it can either 1230, which is equivalent to nickel, or in the aluminum range which is 660, or it may be in between. But because surprisingly there are certain elements which has this property, which we call it as a intermetallic compounds. Okay, so this is the fundamental definition of it. So this is one example. I can give one more example, because most of the time even we see that intermetallics means aluminides. We call intermetallic aluminides. The metal can be anything. The metal can be nickel, metal can be copper, it can be titanium, it can be iron, it can be any other hard metals. But on the other hand, the another material used to be most of the time aluminide, because aluminium is playing the major role. That's why if you see that aluminum alloy is playing a very big role in aerospace applications, high-end cars, so all those things. Okay, so coming back to here, so another example I can say aluminum, which just now I said around 660 degrees centigrade. Another material we can say magnesium. Okay, magnesium is known to be very light metal. So magnesium having the melting temperature of close to 300 degrees centigrade. So now again 300 degrees centigrade magnesium, 660 aluminium, I am diffusing it together, I am casting it together. So again I am expecting a material which is magnesium aluminide, MgAl, have a melting temperature of only 220 degrees centigrade. So this 220 degrees centigrade melting temperature of this particular alloy magnesium aluminium, which is lower than even magnesium, which is lowest. If you see in the previous case, the nickel aluminum alloy is higher than the nickel, which is only 1230. So there are certain materials, there are certain combinations which are known to be intermetallics, and this is what the topic of interest for today. I mean, I have actually two sessions, two parts. So due to time factor, I will see how it goes. So this is the first part. I hope the definition is clear and we can at least little bit understand that what is actually intermetallic compounds, or we known to be IMC. Okay, and in the picture I am also showing that whose crystal structure differs from that of the other constituents, and I will quickly go through because I have many slides, but due to time factor I will see how. Okay, so this is a normal crystal structure. So it forms at one particular phase and then slowly changing. You know, normally we say from BCC to FCC, body centered cubic to face centered cubic, which makes the system to be more stronger or more higher strength. And this is what happening in the intermetallic phases, which make them, even though the two individual components have certain property, the resultant material will have a higher property. Okay, so these are all various things. Aluminium is the common one, which can be added with gold aluminide, and then gold aluminide with the different combination. So I will tell that why it is gold aluminide so special. So today everything is, we call modern world and technology world. We are mostly depending on smartphone, laptops, etc. If you happen to have a laptop which manufactured at least reasonably 2000 and before, maybe in India we have to say even 2005, because normally it introduced in overseas and then coming in. So why I am saying that Because in that particular digital devices, the soldering at the nano level, soldering, I mean, this is what we call the wire bonding. Wire bonding, once again, no need to think of so high. It is nothing but soldering. What is soldering? Diffusing or, soldering two wires together. But two wires together in the macro scale or in the normal scale, we can use the normal soldering method. But if the connections are too small, of the order of either micro level or nano level, we cannot do the normal soldering, because the normal soldering paste and the bump itself will be of certain micron level. So when we want to go up to the nano level, then the usage of material used to be high. So then we know that gold is one of the malleable materials. Gold is one of the malleable material. Even for 1 gram of gold can be stretched up to 1.7 kilometer. So these are all not a proven data, but it can go up to that. This is the nature of gold. So 1 gram of gold. So that's why normally in Indian scenario, we are using gold as an ornament, which can even gives like 3-4 grams of gold can give multiple, design chains, bangles, whatever it is. So coming back to our point, science. So gold is one of the malleable material whereby we use gold aluminide as an intermetallic material, which we used in wire bonding. A technique is well known in any digital applications where we call it as a nano soldering. Of course, the method all is there. I'm just giving you an overview. So in that case, what happened? Gold is used in every, let's say if I'm purchasing a laptop, coming back to the point that I said, minimum 4 gram of gold is used for all the inter-circuitry. Once again, please stop it. Don't take it off today's laptop. No more we are using gold. That's what I said. It all, at least, 98, 2000 before that. Then in the early 2000, there is a new revelation comes in the mobile and laptop technology, whereby now we are no longer using gold in any of the digital devices as a soldering material or wire bonding material. What we are currently using is copper aluminide. This is also one of my research. Okay. So coming back to that, what is actually then wire bonding? Wire bonding is a joining technique to produce discrete electrical contacts. But because the contacts are too small, of the order of either nano level or even sub-micron level we cannot use the normal macro level soldering technique. Then we have to use the techniques such as thermocompression, thermosonic, ultrasonic, etc. And that is where the gold aluminides are used, and that's why we are highlighting here. Okay, so this is one of the wire bonding technique, how it is functioning, and this is the picture. So this is actually a magnified picture of a nanoscale one. We can see that all the wires are connected together and then it will be soldered by this particular technique. And this is what we normally call wire bonding. These are all very well known. So due to time factor, I am highlighting this. Hopefully you can all read it through by other means. Okay, these are all wire bonding. I have a small video, I can show that how it will be functioning before I come down. And this is what I mentioned, that why we need to move from gold into copper. Because due to the price, gold price is the one, last at least 90 years or 100 years keep on only in the upcoming trend, increasing trend. So we are not affordable, whereby today's laptops are coming up even 20,000 Indian rupees, etc. means it is not possible to use. So we have to replace the material. And of course, aluminium is still affordable. The major thing is the gold. So the gold wire bonding now removed and replaced with the copper wire bonding. And this is what in today's scenario. So we can see that what is actually this gold and copper wire bonding. Because it's the afternoon session, I purposely included some videos. Rather than me talking, the videos can better give you an idea. So I'll play now. Okay, so what we have seen now is what is intermetallic, and one of the example of intermetallic, which is gold aluminide, which is one of the commercially used material in many. And when the prices of the gold increasing a lot, and we have to find out a replacement material for the gold, and that is where copper is replaced with gold. And of course, by replacing copper with gold, it won advantages and limitations. So that is where one of my research, okay, so this was in collaboration with Infineon Semiconductor, whereas in Malaysia, Malacca, there is a plant whereby 40,000 employees are working in it, in that Infineon Semiconductors. And we had a collaboration with that on this particular project based on my intermetallics expertise, and we have successfully completed. There are few issues, especially on the void formation at the bonding interface on IMC. We have found it. That is my research, which I'm not going to give in detail here. So let me know about how the copper wire bonding changing from gold into copper. What is the current one? So the one we have seen before, you may not be able to see in today's any laptop or any mobile and digital devices. Whereas the one I'm showing now, the copper wire ball bonding, is the one currently happening in any of the digital and mobile devices. How the nano soldering, or we can call it as a wire bonding, taken place. Okay, thank you. So I hope you have noticed something, that the size of the copper wire used is 33 micron, which is of our human hair size. Okay, so here we can understand few things also. That's why normally what happens, let's say our mobile phone, if you drop it somewhere, drop it means not even at the greater height, even from table to chair, something like that. What we immediately look at is actually whether the screen is okay or not. Okay, but the screen is okay or not is only one side. But this is what real problem is, because all the soldering that takes place inside our mobile and laptop, kind of any technologies today, electronics in general, these are all using a nano soldering, and they are so sensitive. And that's how normally what happens once we drop it, though it's externally nothing happen, internally there could be either the bonding broken, wire bonding broken, or some kind of short circuit. So things make it, like the performance or the usage of that, it become difficult. So this is all some information. Okay, the other information, it's purely on our research work. Okay, so I will just tell you that what actually the achievement we have done while replacing the gold aluminide into copper aluminide. Of course, this German-based company have the research unit all over the world. At least they have 17 units starting from Austria, US, Germany, Batam in Indonesia, Japan. So we are one of the team out of one of the 17 in Malaysia, and I am fortunate to be collaborating with them. So this team in Malaysia, whereas the Infineon Semiconductors, and we came up with some solution which is also useful in their decision making. So what is the problem here? When we replace gold with copper at certain temperature, we normally call industrial temperature at 175 degrees centigrade, with the the high temperature storage we call, with the bonding time of 1000 hours, there will be a void formation takes place. Void is actually nothing but bubble, or okay, a gap, small gap. So in between. So this is what, these are all the real TEM pictures, transmission electron microscope pictures. If you see that this length is 10 micron. So that means the border that we are seeing, which is called actually almost even 30 to 40 nanometer, 10 to the power minus 9. So this is where we have found that all these IMCs, and they are coming up with some void formation, which is the issue that normally the copper wire bonding gets more failure, because nowadays industry working about zero defect. Zero defect is not really zero defect, but depends. They call it as 5 sigma, 6 sigma. 6 sigma means 1.7 defects out of 1 million pieces or components or devices, something like that. So in that case, they work on zero defect, means when they started with the initial copper wire bonding, copper aluminum wire bonding, they found devices getting failure, malfunction within 6 months. This was a big trouble. Then the team of researchers all over the world working on it, and then one of the things identified by our team is also void formation, which we have improved by changing or upgrading certain conditions. Okay, so this is actually about my first part, and I was given the instruction from the organizers that I supposed to finish it by 2:25. So I hope with this particular one, I don't want to detailedly discuss about all these our measurements, which are even we can able to match up to 46 nanometer, what is actually fringes, all the information. So I'll pass it to the organizing team there, and I'm happy that if there is any questions or comments, anything be given. So and I'm not moving to my second part, which is transition metal chalcogenide. If maybe 2-3 minutes time given to me, then I will briefly say about it. If not, I will pass it to the organizers. Thank you. This is actually my second part, but I leave it to them.
So you can take 10 minutes, sir.
Okay. Okay. Thank you. So once again, 10 minutes is not really enough, but I will try to give you a summary of what is my second part. I hope the first part is clear, which I just give only one summary. In the first part is about intermetallic aluminates, or we call simply intermetallics, which is nothing but an alloy or compound in a general way, whereby the properties of the new alloy is totally different than the existing one, so which makes us interesting to work on it. The second part is, of course, solar energy materials, which is in India working a lot. Of course, we all know that solar energy is abundantly available, whereby we are lacking of fossil fuels, etc. So this material, like we are working on, is again with molybdenum chalcogenates, or we simply call transition metal chalcogenates. But of course, I have to give some fundamentals in that. So, okay, like this one all I can skip. And if you see that these are the real satellite pictures that took it, from the satellite, this we can see about where is our India, Japan is having a bright spot, Europe, and this is especially the Northern America. So whereby all the bright spot shows that the amount of electricity that we are using. You can see in this picture that even on the left hand side, on the California side, still in the daytime, whereas in the right hand side, it's on the night time. So what we can see here, there is plenty the amount of electrical usage is increasing day by day, and we are depending on certain available things like fossil fuels and natural resources is not really enough. So we have to look for alternative renewable energy materials, whereby we are working on solar materials or solar panels or green energy materials. That's where even my research group also in Malaysia. Okay. So coming back to that, why we need that? The solar panels are today made up of silicon based silicon panels. Why we need to depend on silicon? Because of the semiconducting nature, whereby the outermost shell need to have four valence. I am skipping most of the things. I'll just keep it small thing. Okay, so we all need to know that any material need to be semiconducting material, then the outermost shell should have a 4 valence electron. So in the periodic table, if you see that as per the physical periodic table, group 4 elements are called semiconducting elements, whereby we have seen 4 elements in group 4: silicon, germanium, carbon, and also stannum, tin. Out of these 4, tin is normally behaving like a metal, or its property very close to metal. So we are not considering it as a semiconducting material, even though its outermost shell has 4 valence electron. Of course, carbon is falling under group 4, but either it used to be in graphite, which is a good conductor, or it used to be a diamond, which is a good insulator. So anyway, we are not using it as a semiconducting material. So left with only 2 materials, one is silicon, another one is germanium. Of course, germanium, which has a smaller band gap of 0.67 electron volt, and which is not readily available everywhere, so we are not mainly using it. So we left out with only silicon. Of course, silicon is a very good material, good semiconducting material, which has the band gap of 1.17 electron volt. Being a semiconducting material, we all, at least being a physics student or physics background, we know that the energy gap, or we call that energy gap between 1 to 4 electron volt, are called semiconducting material. Less than 1 electron volt, we call it as a conducting material. More than 4 valence electron, we call it as a insulating material. So coming back to silicon, which is also again widely used, especially in the last 30 years when the mobile and the internet technology comes in, due to the amount of usage, silicon become wider and larger, we have to find out another material. That is what we call an alternating material need to be found out in replacing silicon, which becomes so expensive. Just to give you a word, we call as a silicon wafer. Okay, a silicon wafer in early 2002, 2003, during my PhD time, it was only $300. We call a silicon wafer in a circular shape. And today the same silicon wafer is $17,000, the same size of 8-inch silicon wafer. Just imagine that from 300 to 17,000 is about 60 times increase the price. But on the other hand, if you look at the electronics part, the prices are not increased a lot, okay, due to maybe mass production, many reasons. But coming back to our point, because we depend on silicon as one of the major material in semiconducting or solar energy materials, we have to change it. Okay, so this is how we are working on alternating materials, whereby we found that where the silicon property can be replaced. And that is what we call transition metal chalcogenides is one of the material. Okay, so with this introduction, I think I stop now. Thank you so much. Sir, good afternoon, sir. Hello, sir. I think I reach out my time that I received a call from organizers. I hope if that is so, I stop with this. Thank you.
Any questions from your side?
Participants in online also you can ask. So,
Sir, good afternoon, sir.
yes. Who's it speaking?
Yes, sir, what is it, sir?
Someone from the online side, it's guess. I think yes. Yeah, that's all.
Professor, it is very informative session. Thank you for your valuable sharings. Thank you, Professor.
Anand, thank you very much.
Thank you, sir. Thank you, sir. So can I stop sharing, sir?
Yes, sir.
Okay, thank you.
Thank you. Professor Chancellor, are you able to hear our voice? Are we audible? Professor Dr. Asakumar Muthupandiyan. Wow.
Okay, I think you have a control over my mic, so now I can speak. So can you hear me?
Hello.
Hello, can you hear me now?
Yes, sir. Yes, Professor.
Okay, it looks like you had unmuted me before, so I'm ready when you are ready, so I can give a talk, so no problem.
Respected Professor Chancellor, are we audible to you? We are able to
Yes,
hear your voice.
I can hear you. I'm not sure whether you can hear me.
Okay. Thank you. Thank you.
Do I start my talk or do I wait?
It's our pleasant duty to invite Professor Dr. Asakumar Muthupandiyan, the Director for the Global Center, Research Center at New Delhi, and the Pro-Chancellor, Vice Chancellor, Deputy Pro-Vice Chancellor, University of Melbourne, Australia. So it's a civil. So it's a great honor for us to have professor in our mid. The professor is a subject expert in applying ultrasounds to the various types of biological materials. He was a very good researcher in those days, right from the beginning onwards. Maybe I think his research career started nearly 30 to 40 years back. And he is having a long standing continuous output in the field of research in the form of high impact factored journals in the Scopus or Web of Science indexed journals. To his credit, professor is having so many patent rights. He held various administrative positions at the University of Melbourne, Australia. He is a very well reputed international scientist who is sought of for this subject materials, especially the interconnection between ultrasound and material science. So we are lucky enough to have professor in our midst for this valedictory function. So there was a lot of bonding between professor and our department. Our department is having a long range of tradition in the ultrasound. So the impact of ultrasound is very much essential to study the various properties and molecular interactions in the biological substances. So the techniques which allows the invasive nature to explore more in the biological substances is the need of the hour. So we don't have any other techniques apart from the ultrasound or non-destructive techniques, especially to test or characterize or synthesize the biological substances. So ultrasound is a versatile technology which has been used over the century. So now professor is having a wonderful research activities. Most of his researches are application oriented or industrial oriented. So in that aspect, the professor is the right person to chair this international conference valedictory function. Because of his lecture, the students and research scholars community in India will be benefited by and large. I welcome Professor on the behalf of the Department of Physics, SJC College. Welcome, Professor.
Thank you very much for the kind introductions. I'm trying to share my screen. Give me a minute, please. Can you see my screen that I'm sharing?
Yes, sir. It's good.
That's good. Thank you. Thank you for the kind introduction and also for kind introduction by Professor Johnson. I'm really pleased and honored to be at this function and also share my research work that I have been doing in ultrasonics area for the past close to 30 years or so. First, I would like to kind of give a brief introduction about the Melbourne University. The University of Melbourne was established in 1853, and it is the second oldest university. Maybe I have to go a step back. About myself, I am from Madurai. I did in fact, the early studies, a part of my studies in Trichy at Bishop Weber College. And then most of my undergraduate, postgraduate studies are at Vijayawada College, and then did my PhD at the University of Madras. After a few years of postdocs, I moved to Melbourne. So I started my position at Melbourne in early 1996. So it's almost like 30 years or so I've been at the University of Melbourne. I'm basically a physical chemist. So most of my research is, as you will see, in ultrasonics area, primarily on materials, biomaterials, food processing, and energy and environmental related research. So coming back to the University of Melbourne, as I said, it was the second oldest university established in Australia in 1853. And you can see in this picture, we have some colonial buildings and also modern buildings for teaching. A little bit of statistics. We are ranked number one in Australia for the past 20 years or so. Globally, 14th as per the QS ranking. And other rankings put us in 32 or 34. Again, we are the kind of top 40 globally ranked place in the past kind of 15 years or so. The university has about close to 60 to 70,000 students on campus. Out of that, about 40% are international students from about 100 different countries. We have also a large alumni, including India, close to kind of 500,000 people. The picture that you see here is the main campus of the University of Melbourne. And what you can see here is the city center, which is south of the Melbourne University campus, or we are located north of the city. And it's about 10 to 15 minutes by walk. And majority of the teaching departments or research departments are clustered around here. We also have a very, very strong medical precinct. The picture on the left shows the main entrance to the university. What you see here as welcome and the Omanchika. So the language used by Aboriginal people is Omanchika, which is for welcome. As you know, the Australian land is owned by traditional owners, the Aboriginal people. So we quite often recognize their contribution to the education, in particular Melbourne University. The Melbourne University has about 7 different campuses. The main campus is the Parkville campus, which is the picture that you see here. We also have some campuses in and around Melbourne. South Bank is mainly for arts, and also Werribee is mainly for some veterinary science, and other campuses are more for purpose-built, either agriculture or horticulture kind of things. So that's a kind of brief introduction about the University of Melbourne. As I was introduced, I have 2 different roles. Currently, I'm I used to be the head of the school and also assistant deputy vice chancellor. Recently, I took over two different roles within the university. They are full-time roles in the chancellery. One is the director of Melbourne Global Center in Delhi, and the second position is the deputy vice chancellor international for South Asia and Middle East. That's all. I have some background information for you. And now I'm kind of trying to introduce the sonar chemistry or ultrasound part. I'm guessing majority of you have some, my understanding because the School of Physics who has organized this, who have some kind of background in chemistry and physics. Just to kind of introduce you to ultrasound, the sound waves, as you know, have different frequencies. The frequency range 20 hertz to 20,000 hertz or 20 kilohertz. That's the range our ear, human ear, can respond or hear. Below that, infrasound is used for communication by some animals. Again, over 20 kilohertz or ultrasound is used for communication by other or navigation by other animals. Majority of you would have heard the word ultrasound for scanning purposes, one of the pictures that I show here. So other than scanning, we can also use ultrasound for doing chemical reactions and for material synthesis. So my today's talk will be a bit more into chemistry and also materials and biomaterial, including biomaterials. I'm hoping that you will be able to follow, even though you may not have some background information in chemistry, if you are more into physics. I'll try my best to kind of make it simple. Okay, so if you have ultrasound going through a liquid, it can be water, it can be any organic liquid. As you know, the sound waves are passing through by means of compression and rarefaction waves in terms of sine wave, as you can see here. And all the liquids will have dissolved gas molecules. Some of these gas molecules will coalesce to form small bubbles. So we have a bubble in the liquid, and if we have the negative pressure around the bubble, when the liquid around the bubble is experiencing the rarefaction cycle or the negative pressure, then the bubble will be forced to expand. And when the next compression cycle comes, then the bubble will be forced to shrink. But during this expansion phase, the dissolved gas molecules and also the solvent molecules will diffuse into the bubble. So during the compression phase, some of these gas molecules will come out, but the amount of gas and solvent molecules that diffuse in during the expansion phase dominates over the amount of gas or solid molecule diffuse out during the compression phase. So in other words, there will be more and more molecules accumulated inside the bubble due to a process called rectified diffusion. It is a very intensive process, but I don't have time to go through the rectified diffusion process. But what you can accept at this stage is the bubble, when it oscillates in response to the fluctuating or oscillating pressure wave, it not only oscillates, but also grows in size. It grows towards what we call a resonance size. And once it reaches the resonance size or size range, then the bubble is forced to grow to a maximum, which is what you see in the video clip just below that. You can see the bubble is growing to a maximum and suddenly collapses. The growth is relatively slow. The collapse is relatively fast. The collapse happens much in faster time scale, within a microsecond time scale. And that collapse is what we call a near adiabatic process. Thermodynamically, when you have an adiabatic process, there is no any heat or energy lost to the surroundings. So what happens is when the bubble is collapsing, the volume is kind of decreasing. When volume decreases, again, going back to simple thermodynamics that you may have learned in school or in undergraduate classes, the work done by a system is equal to P delta V. The delta V term here corresponds to the volume change. And that volume change occurs when the bubble is collapsing. And when that volume change occurs very quickly, then the process becomes adiabatic. So all the energy that is generated due to this volume change is converted into heat. So what happens is when the bubble, at the end of the collapse of the bubble, the bulb temperature within the bubble reaches of the order of few thousand Kelvin. The measured temperatures are anywhere between 1,000 to 10,000. Theoretical estimates can reach up to 100,000 Kelvin. Being physicist, you may want to know that people are trying to, for example, increase the temperature by, forcing the bubble to collapse much faster under much stronger adiabatic conditions to generate nuclear fusion. So if we can reach very, very high temperatures of the order of, say, million degrees, under right conditions, you may be able to induce some nuclear fusion reactions within this bubble. It's an active research area in physics. We don't want to go too much into the details. And because of this high temperature and also molecules being kept inside the bubble when it is collapsing, the high temperature or the heat can promote the molecules from ground state to higher energy states. When the higher energy state molecules return to the ground state, then that extra energy, the energy difference between a higher energy state and the ground state can be released as light. That light emission is called sonoluminescence. Basically, it's a luminescence process induced by sound waves, so that's why we call that sonoluminescence. In my today's talk, I'm not going to talk about that. We are going to more focusing in sonar chemistry. Again, when you have high temperatures and also chemical species like water, oxygen, nitrogen, etc., you can induce chemical reactions. I will come to that point a little bit later. In addition to this radical generation, light emission, there is also shock waves generated, other shear forces generated. For example, because there's a large volume change, the pressure inside the bubble can be of the order of 100 to 1000 atmospheres. After the collapse, that pressure is released back into the solution as a shock wave. And that shock wave can make mass transfer effects that can be used for some processes, which I will highlight later on. And also, when the bubble is collapsing asymmetrically on a surface, you can see this at the bottom photograph, a microjet, liquid microjet can form. That liquid microjet has very, very high kinetic energy, even though the mass may be low because of the speed being very high. That kinetic energy can be used for, again, mass transfer purposes or making changes to the surfaces and so on. So you can see that we have, due to this, what we call bubble oscillation, the process of growth and collapse is called cavitation. We call that acoustic cavitation because it is generated by acoustic force. So the acoustic cavitation process not only can generate radicals and light, but also generate some physical forces that can be used for various applications, which I will highlight later on. I'm hoping that you'll be able to see this video clip that I'm playing. What we have here is a bubble trapped in a capillary, and that bubble is oscillating, which is being driven by a transducer at the bottom. So this capillary tube is about 400 microns in diameter. And you can see how strong the shear forces are around the bubble when the bubble is oscillating. So here we have some silica particles that are moving around. But those silica particles, if you assume that instead of those silica particles, if you have molecules, the molecules are moving around very fast. And again, if you have some chemistry knowledge or chemical kinetics knowledge, you can increase the rate of chemical reactions by increasing the collision frequency or mass transfer, which can also be achieved. In the second video clip that I'm showing here, what you see is a bit of water, a bit of oil. I have an ultrasonic horn that operates around 20 kilohertz coming from the top, positioned right at the interface between oil and water. So again, due to that mass transfer effect that I spoke to you about, shear forces and other things, they can be used to make an emulsion. And this is used heavily in a number of industries. And you can see how quickly an emulsion can be formed. Basically, the oil droplets are dispersed into the aqueous phase. And that kind of emulsions are used in various applications, including in biomedical and food processing and so on. This particular slide is showing what kind of chemistry can happen. as I told you before, if you have water molecules inside the bubble, and because of the high amount of heat being generated, the heat can decompose the water molecules to generate hydrogen atom and hydroxyl radicals. This is, instead of water, you can have other organic solutes, for example. Okay, but I'm just going to show you here water as an example. If I decompose water due to the heat that I generate within the bubble, then I can generate hydrogen atom and hydroxyl radicals. Hydrogen atom, as you can see, is a reducing agent. Hydroxyl radical is an oxidizing agent. So in principle, I can do oxidation and reduction reactions, and almost 100% of chemical reactions are oxidation reduction reactions. So we can do lots of chemistry, including making use these radicals for making materials. So with that background, what I'm showing in this particular slide is what are our various projects that we have been doing in the past kind of 25 years or so. What I have shown is some of the basic aspects of acoustic cavitation, and the slides that I showed did not provide all the information, but basically we in my case, my group has spent about 10 years or so to understand the basics of acoustic cavitation. With that basic knowledge, then we could kind of expand into applied research, applying these kind of processes for energy, environment, health, and food applications. For example, I can use these physical and chemical forces to synthesize functional nanomaterials that can be used for catalytic applications or any other applications. I will highlight them later on. I can use them for food processing to improve the nutritional value of food. I can use them for wastewater treatment. If I have contaminated water, I can use the oxidizing radicals to decompose the contamination or organic contaminants. I can use them for processing, for example, making emulsions, making crystals, or I can make them use them for encapsulating and delivering nutrients and drugs. So I can use them for biomedical applications, but also for food applications. So I will not have time to go through all the applications today, but I will try to highlight some of the applications. Okay, the first part, I'm going to show you some inorganic materials, how to make some metal particles or other materials. I'm taking very simple examples. There are very complex examples, but I'll need more time to explain to them to you, but I'm just taking a simple example. Here, what we are trying to do is we are trying to make metal nanoparticles. I'm showing gold metal nanoparticles as an example. Using a similar approach, I can make any type of metal, whether it is platinum, palladium, ruthenium, what are the type of metal that you want to make. The chemical reaction looks simple, but it is not an easy mechanism that I can explain to you. Simply what we do is we take the metal salt in water. In this case, AU represent gold. So I'm taking gold chloride solution. And if I sonicate gold chloride solution, what I see is you can look at this absorption spectrum. Before sonication, I do not have any absorption in the range 500 or 450 to 700. As I start sonicating, I have an absorption band that appears around 530 nanometers. That absorption band is due to the Plasmon absorption band of the gold nanoparticles. So how these nanoparticles are produced? As I already told, if I have water, water decomposes within the bubble to form hydrogen atom. The hydrogen atom can then diffuse out of the bubble, react with the gold ion. Gold ion has 3 oxidation state, 3+. So 3 hydrogen atoms will provide 3 electrons to the gold ion to form gold atom. The gold atom then can agglomerate to form gold nanoparticles. It's a very simplified mechanism. Okay, so you can use 20 kilohertz or higher frequencies. I'll kind of quickly highlight the frequency effect in the next slide. So I can also increase the rate of the reaction by knowing some chemistry. For example, as I told you, hydroxyl radicals are oxidizing agents. Here we are doing a reduction reaction. We want to reduce the gold ions to gold zero by adding a small amount of organic solute like ethanol. I can convert the hydroxyl radical into an alcohol radical. This alkyl radical or alcohol radical is a secondary, as a reducing agent. So by knowing a little bit of chemistry, I can convert the oxidizing radical into reducing radical. That way I can increase the overall rate of formation of gold. So you can see that compared to water, when I have alcohol, I have higher amount of gold produced. So I can play some chemistry here also. I can use my chemistry knowledge to produce some gold particles. The microscopy, electron microscopy picture that you see here shows that the particles that we produce are anywhere between 20 to 50 nanometers, and they have different shapes. Some of them are cylindrical, some of them are triangular, some of them are spherical, and so on. Later on, I will highlight how to control the shape of the particles and size of the particles. So here, what I'm trying to show you is how to control the size of the gold particles that we produce. So here, for example, if you look at this particular plot on the right-hand side at the bottom, you can see that by changing the ultrasound frequency, I can change the size of the particles that I produced. If I use 20 kilohertz, I produce large particles. If I use 200 to 400 kilohertz, I produce small particles. When I go to high frequency, like 1 megahertz, then the particle size increases. And that is pretty much is related to, as you can see here, this hydrogen peroxide yield is a function of sonication time for different frequencies. That tells that how many primary radicals, the hydroxyl radicals and hydrogen atoms that we generate. So what you can see here is that 20 kilohertz produces very low amount of radicals. 300 kilohertz produces very high amount of radicals. 1 megahertz produces, again, low amount of radicals. So the highest amount that we get is the highest amount of radical production is around 200 to 400 kilohertz. So if I use very high amount of radicals, then I produce more gold particles that produces smaller size particles. Again, those who are working in materials area, you know that when you try to form particles, there are two competing processes, nucleation and growth. If you can increase the nucleation rate, the particles will be smaller. If you increase the growth rate compared to the nucleation rate, the particles will be much larger. So when I produce large amount of radicals, the nucleation of the gold particles, the nucleation rate is higher. Higher the nucleation rate, smaller is the particles. So basically what I'm trying to show here is that by controlling the frequency, I can control the size of the metal particles or metal nanoparticles that we generate. I think I don't want to go too much into the details of the mechanism because we don't have time. I have to cover quite a bit of slides. But basically, I can explain to you why we produce large amount of radicals around 300 kilohertz. It is a combination of the number of bubbles. For example, when you use high frequency, as physicists, you know that as you go to higher and higher frequency, the wavelength decreases. When the wavelength decreases, number of standing waves in a given liquid increases. As you increase the number of standing waves, the number of antinodes in the liquid increases. When you increase the number of antinodes, then you increase the number of cavitation bubbles. If you increase the number of cavitation bubbles, you increase the number of radicals produced. So here it is a schematic scenario between low frequency and high frequency. The photographs shown below are the real-time picture taken with two different frequencies. The sonoluminescence coming from these cavitation bubbles. You can see that at low frequency, you only have 3 active regions. At very high frequency, you have large number of active regions generating cavitation process. So that is the reason for this increase in the radical production from 20 to 300. But then when you go to very high frequencies, there is another factor coming into picture. The bubbles are oscillating too fast. there's no time for water to evaporate. So if you don't have time for water to evaporate, then if there are no water molecules in the bubble, then you will reduce the number of radicals. It's a very simple explanation. And so simply what we are trying to show here is that the size of the particle is proportional to or inversely proportional to the rate of reduction, okay? Here what I'm trying to show you is, okay, if you are again working in this nanomaterials area, you don't have to use sonochemistry to make metal nanoparticles if you're simply looking for large quantities of metal nanoparticles, because you can use simple chemical methodologies. For example, you can use sodium borohydride or ascorbic acid, those kind of things to make large quantities. So sonochemistry may not be economical if you want to make single metal nanoparticle in large quantities, but there are specific cases where sonochemistry can play a role. One example is I'm showing a methanol fuel cell. The methanol fuel cell basically has both anode and cathode made of carbon, and these carbon electrodes are deposited with platinum nanoparticles to increase the electron transfer processes. Okay, so what happens is the methanol gets oxidized. During that process, carbon monoxide is produced as an intermediate product, and carbon monoxide has a very strong affinity to platinum. And so carbon monoxide will not leave out of the platinum surface, poisoning the catalyst or the electrode. So the whole process comes to a standstill. So basically the electrode gets poisoned. Those who are working in electrochemistry, they found out that rather than having platinum single nanoparticle, if you have platinum ruthenium alloy nanoparticle, then ruthenium can convert the carbon monoxide into carbon dioxide. So there won't be any poisoning that will happen. So our aim here is to use sonochemistry to make platinum ruthenium alloy nanoparticles, which are about less than 5 nanometer in size. Conventional processes cannot do this process. If you want to make bulk alloy metals, then you can melt these metals and then mix them. But in the nano size, less than 10 nanometers, it is very difficult to make by conventional methods. So what we have done is we have used ruthenium chloride and platinum chloride in right proportion. And by controlling the rate of reduction of ruthenium and platinum, we could make both 2 nanometer ruthenium platinum alloy nanoparticles, which were used in this kind of methanol fuel cell electrodes to overcome this problem. So this is one unique case where sonochemistry can be is the only option for making alloy nanoparticles. So the next example, I'm trying to show you how to control the shape of the particles. For this purpose, we are using a focused ultrasound, which is called high intensity focused ultrasound, or HIFU. This is used in medical for therapeutic processes. Say, for example, if we have blood clot or kidney stones, then the focused ultrasound can be used to generate strong cavitation at a single point, say, for example, within a millimeter range. And that physical forces that I showed you before can then, the cavitation generated physical forces can be used to break down the kidney stones or the blood clot without any surgery. So that is the purpose of HIFU. But here we are using that high intensity focused ultrasound for the purpose of controlling the shape of the particles. For example, by changing the power using the HIFU, if you use 30 watts, we can get spherical particles. If you use 50 watts, we can get octahedral particles. If you use 70 watts, we can get cylindrical particles or rod-like particles. And again, those who are working in nanomaterials, you know, the color of the solution is influenced by the shape and size of the particle. So you can see that when it is spherical, it is kind of pink in color. It is in rod-like, it is blue or purple in color. Okay. So again, I don't want to go into the mechanistic details. We don't have time. But what I have shown to you is we can control the shape and size by playing with the various ultrasonic parameters. Here, another example again, by using some biofunctional molecules, we can also control the shape of the gold particles. We can get triangular or hexagonal kind of things. I think I want to move on to other examples to kind of make sure that you get an overview of various things that we do, not just kind of metal particles. Here I'm just trying to show you one example where we can use both the radicals and the physical process to make polymer nanoparticles. Again, polymer nanoparticles are used in various applications, including in paints and also in biomedical applications. And it's a very complex chemical kinetics. I will try to skip the kinetics part of it, just come to some of the conversion or important aspects of polymers. So the polymer industries, when they use, I'm guessing you know what polymerization is. You take a monomer molecule and then you use a initiator to initiate polymerization, and then the monomers join together to form a big polymer. Majority of the things that we use every day, they are polymer-based materials. Whether it is the computer that you are using, or clothes, or benches, anything that you see in everyday life, they are polymers. So the polymer industry, has a large economy play in every country. So here, when they try to when they try to synthesize polymer, they need to make sure that the molecular weight of the polymer remains constant throughout the reaction time. So if I'm going to replace the conventional method using ultrasound method, I need to make sure that the molecular weight does not change as a function of reaction time. So you can see that pretty much from 0.5 to 4 hours, the molecular weight does not change. What is critical here is that if I have a polymer that is heat responsive, for example, some polymers will be, their properties will change. When you heat them, then conventional heating or thermal polymerization process may not work. So for example, if you take a conventional reaction, in this case, we are using styrene as a monomer. If you use that and then try to use heat to convert the polymer at room temperature 25 degrees, you can see the conversion is only 10%, even after 4 hours. They have to increase the temperature from 25 to 65 to increase the overall conversion process. Whereas if I use sonication process, where we are creating our radicals are used for making the polymers, you can see that even at 25 degrees Celsius, I can achieve 80 to 100% conversion, which means for those polymers which are heat sensitive, sonochemical method is better than conventional thermal method. And this is the mechanism involved. So I think I already showed you the picture how to make an emulsion here, for example. So when the monomer is dispersed using this emulsification process that you saw, you get the monomer droplets, and then you have in water cavitation bubbles generating radicals. Radicals then can react with the monomer to generate monomer radicals. The monomer radicals can diffuse into the monomer droplet to convert them into polymer particles. So by controlling the size of the monomer droplet, I can control the size and the polymer size of the polymer and also molecular weight of the polymer. Again, there's a kind of specific mechanism involved in terms of how the ultrasound is generating the emulsion droplets. I'll try to skip that because I think I only have another 10 minutes or so to go through some examples. So using this process, for example, I can make magnetic nanoparticles. In this case, for example, I use magnetate iron oxide particles, put them into the monomer. When the monomer droplets are generated, the iron oxide particles are also part of the monomer droplets. So when I convert the monomer droplet, then the iron oxide particles are embedded within the polymer particles or latex particles. and the whole solution becomes magnetically active. So if I can use this process, for example, if it is a biofunctional material that I can use to increase the magnetic activity, then I can use this kind of process or solution for MRI imaging and other biomedical applications. The next example I'm going to quickly go through is polyphenolic nanoparticles, which are used, as you can see, in various applications. So what we can use here is we can take some simple molecules which are biofunctional and convert them into nanoparticles. So what the literature shows is that if you're trying to take, say, for example, tannic acid, which is basically a polymer or polyphenol molecule, they have very, very high antioxidant capacity. But if you just take tannic acid or any other polyphenolic molecules as it is, like, they're there in all fruits and vegetables, they're not staying in the stomach long enough for them to be absorbed. And what the studies are focusing now is that if you convert these molecules into some nanoparticles, then nanoparticles can stay in the stomach for much longer time, slowly releasing the polyphenolic molecules into our system that has a proper biofunctional effect. So here what we have done is we have used a sonication process. For example, we took this molecule and converted using sonication or the oxidation radical that we generated, we converted them into nanoparticles. Again, for those who do not have chemistry knowledge, it will be difficult for you to understand this. But what I would like to highlight here is that this methodology can be used to increase not only the nutritional value, but also for drug delivery purposes. So you can use some molecules which are active against cancer, for example. Then you can use this process to convert them into small nanoparticles. And that way, the efficiency of the drug intake will be much, much higher. The process is quite complicated. It involves the hydroxyl radicals that we generate, but also it involves the heat that we generate when the bubbles are collapsing. So a combination of heat at the interface of the bubble and the radicals that we generate as a combination of these two leads to the formation of this kind of dimer, trimer, and some sort of oligomers, which self-assemble to form these kind of nanoparticles. I know I'm rushing. I just want to give you an overview at this stage, but for those who are interested, please feel free to contact me. I'm happy to share some papers which will give you full in-depth knowledge on these things. The last example that I would like to go is something on the encapsulation using ultrasonic processes. So here, for example, I can use a biopolymer like a protein or a carbohydrate to encapsulate drugs or any nutrition like vitamin and so on. And then these kind of encapsulated particles can be used to deliver either the drugs or nutrients in various matrices. Okay. So what you see here is we have encapsulated vitamin E in this particular case, or not, in this case, fish oil in lysozyme shell. You can see that the shell is quite thick. And if you break the shell, the liquid is still inside as the liquid, which means the functional, physical, and other properties of the nutritional or biomedical materials are preserved during this encapsulation process. And then the encapsulated materials can be used for, as I said, for delivering nutrients and drugs. The chemistry behind this is quite kind of complex. So the proteins go and absorb either on the air liquid or liquid-liquid interface, and then we simply cross-link them to form this kind of microspheres. So in here, for example, the microspheres are loaded with a drug called doxorubicin, and the red dye that you see is due to the doxorubicin that can be used, for example, for cancer treatment. So the difference between simply injecting doxorubicin compared to the microspheres is that when you simply inject into the blood, they go everywhere. But when you inject through this kind of microsphere, we can functionalize them and make them deliver locally where they have to be delivered. So it's kind of targeted drug delivery process. We can also encapsulate or load these microspheres with some metal particles, which have some antimicrobial activities. Again, we can use them for biomedical applications. I'm just going to skip this because basically I can control the shape and size of these microspheres for various applications, but I'm just going to finish with two applications. One of them that we did for the Cadbury chocolate people for encapsulating flavors using this similar kind of approach. So simply what you do is you take any flavor, use the methodology that we developed to encapsulate these flavors and then put them into cocoa butter and use them for chocolate making. So end of the day, the chocolate that you make through this process, it can have the flavor. Instead of flavor, you can have a nutrient like vitamin or anything. So simply what we are trying to do is we are trying to make these chocolates a bit more healthier by using this kind of encapsulation technology. By extending this, we did a project for Gates Foundation to encapsulate, in this particular case, vitamin and other nutrients. And, the project was funded mainly to address kind of malnutrition among children in underdeveloped and developing countries. That's why Gates Foundation was very keen to support this. So what we have done in this particular case is using our encapsulation methodology, we encapsulated vitamins, and then we incorporated those kind of encapsulated microspheres into flour that, for example, you can make chapatis or bread or biscuits. Even after you process this, flour, so say, for example, you made biscuits, these biscuits can be stored for a year or two without any proper storage conditions. In some of the underdeveloped countries, they don't have refrigerators, they don't have, fresh fruits and vegetables. So for them to take this kind of nutritional food, they can be delivered through this kind of biscuits, which can be stored under any temperature conditions, any other environmental conditions. Until you eat them, the nutrients are kind of preserved for years. Okay, so this is another kind of applied project that we did, which has some positive impact for the community. A similar kind of approach we have taken for other products, like in this case, we are trying to make emulsion gels without adding any kind of complex chemicals. So normally, when you want to form an emulsion gel, like cheese, buttermilk, everything is emulsion gel, cosmetics, pharmaceuticals, and so on. They use large amount of chemicals to make these kind of emulsions, highly heat treated in a plant. But the methodology that we have developed is a simple, no external chemicals added. For example, here I'm just adding some vegetable oil to form an emulsion, just for a demonstration purpose. And then you use that pre-emulsified material or emulsion into a high pressure process and get the emulsion gel. So compared to chemically made emulsion gels, these are green products, highly healthy, no side effects, and so on. Again, we are working with some companies to make these products in commercial scale. So what I have shown you in the last kind of 45 minutes or so, I gave very, very, very high overview of what ultrasound can do or acoustic cavitation do in terms of making materials, biofunctional materials for various applications. And ultrasonic technology is considered as a green technology. Scaling it up is an issue at this stage that some companies and researchers are trying to address. But overall, I think it is an area which is kind of having some kind of future prospects in the next kind of 5 years or so to make specific functional materials for various applications. With that, I would like to again thank Professor Johnson for his kind invitation. Thank you all, all of you for listening to me. I'm not sure whether we have enough time for questions, but please feel free to reach out to me by email if you need some additional information on anything that I told you. Thank you again. I stop here.
Thank you, Professor. Thank you very much for your wonderful presentation. in the very hot topic, that is the major interplay between ultrasound and material science. And before going to the interaction with the scholars, I have some simple clarifications or questions to you. What kind of full frequency, that is a low frequency or high frequency, will be useful for this nanomaterials or to form the nanocrystals or nanomaterials?
Yeah, if you're trying to make, say, metal or oxide nanoparticles, where the chemistry plays a role, then the frequency that is good for is around 200 to 400 kilohertz.
Kilohertz.
Majority is, large amount of radicals. But if you are looking into polymer, for example, if you want to make an emulsion polymer, then you need both the shear forces and also the radicals. For those kind of materials, or even some biofunctional materials, you can use 20 kilohertz. So depending upon the type of materials that you want to make, you can use high frequency or low frequency.
Okay, so depending on the particular type of material, we can select either in kilohertz or megahertz.
Exactly.
You have applied ultrasound to various type of living substances as well as materials. It's quite awesome. I have a simple question. This ultrasound will have its own influence in the sea animals like fish or crabs, especially to increase the growth or to produce more fishes in the sea. The ultrasound will have its own influence, maybe, sir?
Yeah, okay. I think it's a different area. I don't think they have used it for animals, but they have used it for seed growth.
Okay.
So basically, use some, here it is nothing to do with the cavitation. It's more of the physical vibration induces the growth. So people have used it for seed growth in many areas.
It will not have any impact in the yield of fish, sea animals. Fish or
That's an area that has not been explored.
Yeah.
So there's a potential for someone to initiate that research. Yeah.
Not yet explored that area. Okay. We are having a wonderful scientist, international scientist in our midst. Scholars, are you having any questions either by offline or online? You are most welcome. Yeah.
Sir, thank you, sir, for your excellent narration and informative session. My question is, can sonication increase the cytotoxicity of a drug?
Okay. There's a large body of work already has been done on that part. So majority of the work that we have done in collaboration with some biomedical people here shows that if you prepare the material using sonication, because you're not using the sonication to deliver the material, but you are just kind of using the sonication part to convert, for example, the molecules into nanoparticle, and that does not increase the cytotoxicity. And we have some studies reported, so I'm happy to share that papers with you.
Any other clarifications or questions from the audience? You are most welcome. Okay, if you have any clarification, you can contact Professor directly. And to summarize, actually I wanted to introduce Professor at the beginning. The problem is Professor CV is nearly 60 pages. If I am going to give an introduction for Professor, I think the session will end without his lecture. So now at least I want to say some beautiful things, wonderful achievements of our beloved Professor. Professor held various positions across France, Australia, Japan, and Rome in the form of prestigious fellowships and international awards. Professor held many academic and administrative positions, especially in Australia, in the University of Melbourne, and various international governmental bodies. So we can ask a question about the professor. why Professor Ashok Kumar is a resource person and a well-defined function. So he is a global authority in sonochemistry and ultrasonics with extensive research and industry impact. He is a visionary leader in international education and academic collaborations. He is having a proven success in research in translation from lab innovation to industry applications. He is an exceptional mentor and speaker known for engaging knowledge sharing sessions. So he used to have a vast industry and international collaborations. He has key research grants and industry engagements are many. Australian Research Council, Dairy Innovation Group, Food Value Chain Research, CISRO Food Future Flagship Grant, Bill and Melinda Gates Foundation Grant, and so on. He was a designated designed University of Melbourne's India Engagement Strategy. He led the development of joint PhD and dual degree programs with Indian universities. He initiated STEM outreach research program for underprivileged students. So he is having a quite number of publications also. Name a few of the publications effect. He is having more than 600 journals in the Web of Science Scopus indexed journals. And he is also having his search index factor is very high. And he is a fellow of Royal Australian Chemical Institute. He is the editor-in-chief of Ultrasonic Sonochemistry. He is the president of Asia Oceania Sonochemical Society. He is a special awardee for excellence in internationalization of research. And he was an invited panel member at WIPO 2020 Summit. So his research and patents are quite interesting. He authored 523 research publications with a high impact factor. His H index is 86 with 25,500 citations in Scopus. He had many patents. Most of the patents are commercialized in industries. So he is a man who takes the lab to the land. So I thank you, Professor, very much on behalf of the Department of Physics, St. Joseph's College, and the large research community in India. Thank you for your valuable time and presence with us. Thank you once again.
Thank you for the kind introduction again. I'm really kind of pleased and honored to be at this event, and thank you for the opportunity. Thank you.
Thank you, Professor. One question is coming online, Professor. Can I share with you?
Sure.
So there's a question from Tanya. She's asking, how can we detect the side effect of a drug consumption, sir, using ultrasonics?
Yeah, I think that there'll be the study that needs a bit more time. So, for example, we may need a large study involving a number of people. For example, if we inject our microsphere-based drugs, it'll take a few years for us to understand the side effect. But I think the previous question was, will there be any kind of negative effect if you use sonochemistry? Lab studies have shown that no negative effects are observed. But if you want to really understand what happens to humans, then it needs a separate study. So at this stage, I cannot confidently say that there won't be any negative effect because it needs a separate study.
There's one more question from Avinash. He's asking, can you share about the PhD program in the University of Melbourne?
Yes. So the University of Melbourne offers a number of scholarships for all disciplines. There are, each faculty will have a certain number of scholarships for international students. So anyone can apply. When you apply for a PhD program, all the applications will be automatically considered for scholarships. So if you are in the top 10% of the total applicants, then you will get a scholarship. But the first thing that you need to do is you need to identify a supervisor who can support your application. That's the first point. So first you identify who you want to work with, contact them, ask their support later, and then you can apply online. But, again, please feel free to contact me by email. I can send you some links that may be helpful for you.
Any questions or clarifications?
I would like to also mention that, I'm happy to talk to some of your authorities at St. Joseph's to see if we can do some dual degree program with your college, between Melbourne University and your college. Please keep me informed.
Thank you, Professor. I will be in touch with you. Thank you very much. I will be in touch with you. So it's a quite wonderful experience with our great professor, who is a master in ultrasound and material science. So definitely the interplay between ultrasound and material science is the future of the world. And as Professor told, many of the areas are still unexplored. That's the reality. Thank you, Professor. Thank you very much. Thank you. On behalf of the Department of Physics and St. Joseph's College. Thank you. Thank you very much.
Thank you, Dr. Johnson, HOD, for introducing the chief guest and for chairing the session. Your insightful words have set a perfect tone for the prestigious gathering. And of course, a special note of appreciation to our esteemed chief guest, Professor Muthupandi Ashok Kumar, for delivering such a thoughtful, provoking, and insightful address.
Excellence is the gradual result of always striving to do better. Now, it's a time to recognize and celebrate excellence through the prize distribution. We take this moment to appreciate and acknowledge the hard work and excellence of our participants.
To announce the results, I would like to invite Dr. Maggie Diana to announce the results.
Good afternoon. I request Dean of Physical Sciences to distribute the prizes. Sir, please. For the event oral presentation, the first prize goes to Vijayapriya V, Lady Dock College, Madurai. She receives a cash prize of ₹1,000. Second prize goes to Arun Kumar Selvam, National, Taipei University, Taipei. He receives a cash prize of ₹800. He is an online participant. The third prize goes to E. Adira, University of Calicut. She is also an online participant and she receives a cash prize of ₹500. For the event poster presentation, the first prize goes to Yogeshwari C. of DG Vaishnav College. She receives cash prize of ₹1,000. The second prize goes to Ashif Iqbal of Bakwat University. He is an online participant, and Jelsi M, she is also an online participant from the new college, Chennai. Thank you, professors. Thank you. Now we move on to vote of thanks. Once again, good evening to everyone. It's my honor to propose the vote of thanks of the International Conference of Advanced Materials ICAM 2025. I extend my words of gratitude to everyone who contributed to making this program a success. I extend my sincere gratitude to the management for their unwavering support and encouragement in organizing this event successfully. My special word of thanks to today's chief guest, Professor Muthupandi Ashok Kumar, Professor of Chemistry, Department, Deputy Vice Chancellor, International University of Melbourne, Australia, for his valedictory address. My sincere thanks to convener and co-convener of ICAM 2025. A heartfelt thanks to the resource persons, both online and offline, and chairpersons for sharing their valuable insights and expertise, enriching our conference with meaningful discussions. I also extend my appreciation to various committee members, and Joint Secretary for their dedicated efforts in ensuring the smooth execution of this event. A special word of thanks. A special mention to JCICT team for their commendable work in publishing the brochure on the college website and facilitating the registration process through the online link. I sincerely thank Dr. Tamilarasi and Viscom department for capturing the event through photos and videos. And I also thank Dr. B. Kanikaraj, Department of Physics, for providing the AV room and supporting with their infrastructure. My gratitude also goes to the non-teaching staff members for their invaluable support behind the scenes, and to Mr. Velangani and his team for technical assistance with AV support. My special word of thanks to all the research scholars for their support. Thank you very much. Finally, I thank all the online, offline participants, PG and UG students of our department for their active engagement, making this event a grand success. Thank you once again. And an announcement, there will be a feedback link. Please fill the feedback link and you have to submit it by today. Other participants, that is participants from other college, can collect their participation certificate in front of this sale hall. Thank you.
Thank you, ma'am, for your heartfelt thanks. Now let us rise for the national anthem.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल वंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे।
With this, we officially conclude the International Conference on Advanced Materials 2025.
I request the staff all